Some objects in the universe are large, others are difficult to imagine, and then there are a few that quietly break the way scale itself works. Stephenson 2-18 is one of those objects. It is not dramatic at first glance. It does not explode, collide, or race through space. It simply exists, so large that familiar comparisons stop being useful, and even astronomical language begins to feel inadequate. When we talk about stars, we usually rely on numbers to describe them. Mass, radius, luminosity. But there comes a point where numbers no longer help the mind understand what they represent. Stephenson 2-18 lives beyond that point. Before we continue, if you enjoy slow, thoughtful journeys through space, videos designed to be listened to calmly, without urgency, you're welcome to subscribe to Theories Before Sleep. These explorations are made to unfold gently, letting the universe speak at its own pace. This is not a story about danger. It's not about destruction or spectacle. It's about scale, and what happens when something becomes so large that it stops fitting into our mental frameworks. As we move forward, we won't rush. We'll place this star carefully into context, comparing it to familiar objects, then slowly removing those references one by one. Because Stephenson 2-18 doesn't just stretch space, it stretches understanding. Tonight, we're not asking what it does, we're asking what it means for something to exist at a size where comparison itself begins to fail, and will begin very gently. When astronomers first began cataloguing the largest stars in the Milky Way, the idea of big still had boundaries. Even the most massive blue giants, even the bloated red supergiants, could still be placed on charts compared to the Sun and understood through familiar reference points. There was always something larger to compare them to and something smaller to anchor the imagination. Stephenson 2-18 quietly erased that comfort. This star exists inside a massive stellar cluster known as Stephenson 2, buried deep in the Milky Way and heavily obscured by dust. It is not visible to the naked eye. It does not shine dramatically in the night sky. In fact, for a long time, it remained almost unnoticed, hidden behind layers of interstellar material that absorbed its visible light. Only when astronomers began observing in infrared did its true nature start to reveal itself. Stephenson 2-18 is classified as a red supergiant, but that label barely captures what it is. Red. Supergiants are already among the largest stars known, stars that have expanded late in their lives after exhausting hydrogen in their cores. Many famous examples exist, like Betelgeuse or Antares, stars so large that if placed at the centre of our solar system, they would engulf the orbits of Mercury, Venus, Earth, and sometimes Mars. For a long time, those stars defined the upper edge of stellar size. Stephenson 2-18 does not sit at that edge. It pushes far beyond it. Based on current estimates, the radius of Stephenson 2-18 is so vast that if it replaced the Sun, its surface would extend beyond the orbit of Saturn, possibly approaching or exceeding Uranus. Light itself would take hours to travel across its diameter. The Sun, by comparison, would be a microscopic speck inside it, utterly lost and invisible. At this scale, familiar comparisons begin to collapse. Saying bigger than the Sun stops being meaningful. Even saying bigger than the solar system starts to feel abstract. The star is no longer just an object within space. It becomes a region of space, a volume so enormous that motion and distance inside it behave differently than intuition suggests. What makes this more unsettling is not just its size, but its density. Despite its immense volume, Stephenson 218 is incredibly diffuse. If you could somehow stand within its outer layers, ignoring the lethal temperatures and radiation, you would not encounter anything resembling a solid surface. The matter is spread so thinly that, in many regions, it is less dense than the best vacuums humans can create on Earth. This star is vast, not because it is packed tightly, but because it is inflated to an almost absurd degree. This inflation is the result of stellar evolution pushed to an extreme. Stephenson 2-18 is nearing the end of its life. Deep in its core, nuclear fusion has moved beyond hydrogen, creating heavier elements. Each new fusion stage produces less outward pressure, allowing gravity to partially win, while energy released in outer layers causes the star to swell. The balance between gravity and fusion has become delicate, unstable, and exaggerated. The star breathes in slow motion. Its outer layers expand and contract over time, driven by complex interactions between radiation pressure and gravity. These pulsations are not gentle. They eject massive amounts of material into surrounding space, creating dense clouds of gas and dust that will one day seed future stars. Stephenson 218 is not just large, it is actively losing itself. What is remarkable is that, despite its size, the star is not especially luminous compared to some smaller but hotter stars. Its surface temperature is relatively low, giving it a deep red glow in infrared wavelengths. This combination of enormous size and moderate luminosity challenges simple assumptions about how stars behave. Bigger does not always mean brighter. Scale and energy do not increase together in neat proportions. At this point, even astronomers begin to speak cautiously. Measuring a star like Stephenson 2-18 is difficult. Its distance is uncertain. Its outer boundary is not sharply defined. The concept of radius becomes fuzzy when a star's atmosphere blends gradually into surrounding space. Different models produce different numbers, and each estimate comes with significant uncertainty. Yet even the most conservative estimates place it among the largest stars ever observed. This uncertainty does not weaken its significance, it strengthens it. Stephenson 2-18 exists in a regime where our definitions struggle, where the idea of a star having a clear edge starts to fail, where astrophysics becomes less about precise numbers and more about understanding limits. Limits are important in science. They tell us where theories stop being reliable. They show us where assumptions break down. Stephenson 2-18 sits exactly at one of those boundaries. It forces astronomers to ask uncomfortable questions. How large can a star really become before it becomes unstable? Is there a maximum size imposed by physics, or are we simply observing one extreme of a broad continuous spectrum? This star also reshapes how we think about stellar death. When stars like this finally collapse, they do not go quietly. Their cores can implode and rebound in catastrophic supernovae, releasing more energy in seconds than the Sun will emit in its entire lifetime. But in stars as large as Stephenson 2-18, even the mechanics of collapse become uncertain. Some models suggest direct collapse into a black hole. Others suggest partial explosions that leave behind exotic remnants. The sheer scale complicates everything. Another unsettling aspect is time. Massive stars live fast and die young. While the Sun will exist for billions of years, Stephenson 2-18 may have only lived a few million. Its size is not a sign of longevity, but of instability. It represents a brief, violent phase in stellar evolution, a fleeting moment where matter organizes itself into something enormous before gravity reclaims it. In this sense, Stephenson 218 is not a monument. It is a transient condition, a snapshot of physics pushing itself to an extreme, then preparing to collapse back into simplicity. What makes this star especially powerful as an idea is how it warps perspective. When we imagine the universe, we often think in terms of distances between objects, galaxies separated by millions of light years, stars scattered across vast emptiness. Stephenson 218 challenges that by being emptiness itself filled with matter, a single object occupying a region of space large enough to contain entire planetary systems. Inside it, space is not empty. Space is the star. This realization quietly shifts how we think about scale in the cosmos. The universe is not just big because of the distances between things. It is big because things themselves can become unimaginably large. Stephenson 218 does not threaten Earth. It does not dominate headlines. It does not explode dramatically on human timescales, and yet it unsettles something deeper. It reveals that the universe allows structures far beyond what intuition expects. That physics, given the right conditions, does not stop at comfort. This star exists not to be understood easily, but to stretch understanding itself. And as we continue, the question will no longer be how big Stephenson 218 is in numbers. The question will be how something can exist at all when size itself begins to lose meaning. To understand why a star like Stephenson 218 can exist at all, it helps to step away from size for a moment and look at balance. Every star, no matter how small or large, is defined by a delicate negotiation between two opposing forces. Gravity is constantly trying to pull the star inward, compressing it toward collapse. At the same time, energy produced in the core pushes outward, trying to expand the star and tear it apart. What we call a stable star is simply a temporary truce between these two forces. For most of a star's life, that balance is relatively simple. Hydrogen fuses into helium in the core, releasing energy that counters gravity. The star's size remains fairly steady. Our Sun has existed in this calm equilibrium for billions of years. But massive stars like Stephenson 218 were never meant to stay calm. Their mass changes the entire story from the beginning. From the moment a massive star forms, gravity dominates more strongly. To resist collapse, the core must burn fuel at an extraordinary rate. Fusion runs hotter, faster, and more violently than in smaller stars. This intensity shortens the star's life and accelerates every stage of its evolution. Where the Sun has time measured in billions of years, stars like Stephenson 218 measure their existence in millions. As hydrogen runs out in the core, the balance shifts. Gravity begins to squeeze the core inward, raising temperatures and pressures enough to ignite new fusion reactions. Helium begins fusing into heavier elements like carbon and oxygen. Each new stage releases energy, but less efficiently than the one before. The outward pressure weakens relative to gravity. Instead of collapsing immediately, the star responds by expanding. This expansion is not a gentle swelling. It is a dramatic restructuring of the star's internal layers. The core contracts and heats, while the outer layers balloon outward to maintain balance. This is how red supergiants are born. Their surfaces cool as they expand, glowing red and infrared, while their interiors become increasingly unstable. Stephenson 2-18 represents this process taken to an extreme. The star's outer layers have expanded so far that they exist in a regime where gravity barely holds them together. These layers are not tightly bound. They drift, pulse, and shed mass continuously. The star is losing material at a staggering rate, forming thick envelopes of gas and dust around itself. In many ways, Stephenson 2-18 is already dissolving. What makes this especially strange is that expansion itself weakens gravity at the surface. As the star grows larger, the gravitational pull experienced by its outer layers decreases. This creates a feedback loop. Weaker gravity allows further expansion, which weakens gravity even more. The process feeds on itself until something breaks. This raises a critical question in astrophysics. Why doesn't the star simply fall apart? The answer lies in radiation pressure. Even though fusion in the core becomes less efficient, the enormous luminosity of the star still produces enough radiation to support its inflated atmosphere. Photons streaming outward collide with atoms in the outer layers, transferring momentum and helping hold the star together. It is a fragile support system, but it works. Temporarily. Temporarily is the key word. Stephenson 2-18 exists in a narrow window where gravity, radiation, and internal fusion are barely balanced. Any significant change could push it into collapse or trigger catastrophic mass loss. This is not a stable configuration meant to last. It is a brief phase in a star's life, captured by chance. Adding to the complexity is the fact that stars of this size are not uniform. Their interiors are layered like an onion, with different fusion processes occurring in shells around the core. Each layer behaves differently. Each responds to pressure and temperature changes on different timescales. The star is not one object acting in unison, but many interacting regions struggling to remain coherent. This internal complexity makes modelling stars like Stephenson 2-18 extremely difficult. Small uncertainties in mass, composition, or distance can produce wildly different predictions. Astronomers debate whether such stars truly reach the sizes we calculate, or whether our measurements are influenced by extended atmospheres and dust envelopes that blur the boundary between star and space. And yet, even allowing for uncertainty, the conclusion remains unavoidable. Stephenson 2-18 operates at the edge of what stellar physics allows. It also forces a re-examination of how we define a star's size. When does atmosphere end and space begin? For compact stars, the boundary is clear. For red supergiants, it becomes ambiguous. The outer layers are so thin and extended that there is no sharp edge. The star fades gradually into surrounding gas. In practical terms, this means Stephenson 2-18 may occupy a region of space where parts of it are only loosely bound. Some material may already be escaping, drifting away to become part of the interstellar medium. The star is not just large, it is porous. This porosity challenges intuition. We tend to imagine stars as solid spheres of glowing matter. Stephenson 2-18 is closer to a vast, diffuse cloud with a dense core, buried deep inside. Its size comes from inflation, not concentration. This has profound implications for its future. When the core finally exhausts its ability to generate outward pressure, collapse becomes inevitable. Gravity will suddenly dominate, pulling the core inward at tremendous speed. What happens next depends on mass, rotation, and composition. The core may rebound in a powerful supernova, blasting the outer layers into space, or it may collapse directly into a black hole, swallowing much of the star with little external display. For a star as extreme as Stephenson 2-18, neither outcome is guaranteed. The very size that makes it impressive also complicates its death. The outer layers are so extended that they may fall inward slowly, dampening the violence of the collapse, or they may already be so loosely bound that they escape before the final collapse even occurs. In either case, the end will be swift compared to the star's brief life. Millions of years of growth and instability will resolve in moments. What makes this unsettling is how casually the universe allows such extremes. There is no special rule forbidding a star from becoming this large. No warning sign written into the laws of physics. Given enough mass and the right conditions, matter is free to inflate itself to absurd scales, hovering on the edge of collapse. Stephenson 2-18 reminds us that the universe does not prioritize neatness. It allows imbalance. It tolerates instability. It explores the full range of what is physically possible, even when those possibilities defy comfortable explanation. And perhaps most striking of all is how quiet this exploration is. There is no explosion announcing the star's size, no dramatic flare visible across the galaxy. Stephenson 2-18 simply exists, hidden behind dust, glowing softly in infrared, quietly testing the limits of stellar structure. Its presence forces a subtle shift in perspective. The universe is not just vast because of distance. It is vast because it allows objects to become so large that distance loses meaning within them.
As we continue, the focus will move away from how Stephenson 2-18 formed and toward what it represents. Because beyond its physical properties, this star stands as a reminder that scale in the universe is not a hierarchy with clear boundaries. It is a continuum, and somewhere along that continuum, size stops being a number and becomes an experience the mind struggles to contain. When scientists attempt to place Stephenson 2-18 into a broader cosmic context, they quickly encounter a problem that goes beyond measurement. The problem is comparison. Almost everything we understand about stars is built on relative scale. Bigger than the sun, smaller than a cluster, brighter than this, heavier than that. Stephenson 2-18 stretches those comparisons until they stop being useful, not because the numbers are unknown, but because the human mind loses traction. To say that this star could engulf the orbits of Jupiter or Saturn if placed at the centre of our solar system sounds impressive, but it does not truly convey what that means. Planets are distant points of reference. We imagine their paths, their spacing, their emptiness between them. Stephenson 2-18 would not merely occupy that space, it would redefine it. Inside such a star, the idea of orbit becomes abstract. Distance is no longer something you cross between objects. Distance becomes something you experience within a single object. Light itself behaves differently at this scale. A beam of light emitted from one side of the star would take hours to reach the other side. This is not a poetic exaggeration. It is a direct consequence of its diameter. When light, the fastest thing in the universe, takes hours to traverse a single star, that star is no longer just large. It has become spatial. Whereas, this realization quietly shifts how we think about what a star is. Most stars are points of light, even through powerful telescopes. They exist conceptually as sources, not places. Stephenson 2-18 challenges that categorization. It is not just something that shines, it is somewhere matter resides. Somewhere physics unfolds internally over distances comparable to planetary systems. Inside the star, conditions vary dramatically from one region to another. Near the core, temperatures and pressures are extreme, driving fusion reactions that shape the star's fate. Farther out, the atmosphere thins, temperatures drop, and matter becomes so diffuse that atoms rarely interact. The star is not uniform, it is a gradient spanning unimaginable scales. This internal diversity is part of what allows such a star to exist. Stephenson 2.18 is not held together by a single mechanism but by layers of compromise. Gravity dominates in the core. Radiation pressure supports the middle regions. Pulsations and turbulence shape the outer envelope. Each layer obeys the same laws of physics, yet produces vastly different behavior depending on local conditions. This layered existence makes the star fragile in ways that are not immediately obvious. While it appears stable on human timescales, internally it is constantly adjusting, shedding mass, rearranging energy flows. Its surface does not sit still. It expands, contracts, and ripples over time, driven by cycles deep within the star. These changes can span distances larger than entire planetary systems. Mass loss is one of the most critical aspects of Stephenson 2.18's existence. The star is continuously losing material through stellar winds, ejecting enormous quantities of gas into surrounding space. Over time, this mass loss will significantly alter its structure. In extreme stars like this, mass loss is not a minor detail, it is a defining process. The material shed by Stephenson 2.18 does not vanish. It becomes part of the interstellar medium, enriching it with heavy elements forged inside the star. In this way, the star participates in a larger cosmic cycle. Its instability contributes to future generations of stars and planets, even as it moves closer to its own end. Yet the scale of this contribution is difficult to grasp. The volume of material expelled by such a star can rival the total mass of entire planetary systems. Over time, the star can lose a significant fraction of its original mass before it ever collapses. This gradual erosion reshapes its fate, influencing whether it will explode or collapse quietly. What makes this particularly fascinating is that Stephenson 2.18 exists near theoretical limits. Astrophysicists have long debated whether there is a maximum size a star can reach before becoming unstable. Various mechanisms impose constraints. Radiation pressure can blow material away. Gravity can trigger collapse. Rotation can tear a star apart. Stephenson 2.18 sits near where these constraints intersect. This is why it is often described not just as large, but as problematic. It does not fit neatly into models. Its observed size pushes against expectations derived from theory. Each attempt to explain it forces refinements in our understanding of how massive stars behave late in their lives. Even defining its size becomes an exercise in interpretation. Where does the star end? Is it at the point where density drops below a threshold, where temperature changes abruptly, or where emitted light fades into background noise? For stars like Stephenson 2.18, there is no clear answer. The boundary between star and space is blurred. This blurring has philosophical implications as well as scientific ones. We tend to think of objects as having clear edges. Stephenson 2.18 suggests that, at extreme scales, nature does not respect such clean divisions. Objects fade into their environments, categories soften, definitions become provisional. In that sense, the star does not just break scale, it breaks classification. It also challenges intuition about energy. One might expect such a massive star to be blindingly bright, yet its surface temperature is relatively cool. Its enormous luminosity is spread over an immense area, reducing intensity at any given point. This again disrupts simple assumptions. Size does not translate directly to brilliance. Extremes do not behave linearly. This non-linear behavior is a recurring theme in astrophysics. When systems become large enough, new effects dominate. Forces interact in unexpected ways. Feedback loops emerge that stabilize or destabilize structures unpredictably. Stephenson 2.18 is a laboratory for these effects, even though it exists far beyond our reach. It also reframes how we think about rarity. Stars this large are extremely uncommon, not because the universe forbids them, but because the conditions required to form and sustain them are fleeting. Massive stars form quickly, evolve rapidly, and die young. The window during which a star reaches this inflated state is brief compared to cosmic timescales. This means we are observing Stephenson 2.18 at a fortunate moment. Not special in purpose, but special in timing. In a few 100,000 years, perhaps less, it may no longer exist in this form. It will collapse, explode, or transform into something else entirely. And yet, despite this transience, its impact on understanding is lasting. The star serves as a reminder that the universe is not optimized for human comprehension. It allows extremes that stretch cognition. It permits structures that challenge the way we think about size, stability, and identity. Stephenson 2.18 does not need to be the largest star ever discovered to fulfill this role. Even if future observations revise its size downward, even if another star surpasses it, the lesson remains. There exists a regime where stars become so large that scale itself becomes unstable as a concept. In that regime, numbers lose their intuitive meaning, comparisons fail. Objects stop behaving like objects and begin behaving like environments. And that is perhaps the most unsettling realization of all. Stephenson 2.18 is not just something you look at, it is something you would exist inside without ever reaching the edge. A reminder that the universe is not only vast because it is spread out, but because it allows single things to grow so large that they contain entire worlds within them, quietly challenging the limits of understanding itself. As attention shifts from sheer size to consequence, Stephenson 2.18 begins to feel less like an outlier and more like a warning written into the fabric of stellar physics. Not a warning of danger, but a warning of limits, or rather of how close matter can approach them before familiar behavior dissolves. The star's existence forces a confrontation with a question that astronomy often avoids. Not how things work when conditions are ideal, but how they behave when conditions are pushed so far that stability itself becomes questionable. One of the most unsettling aspects of Stephenson 2.18 is how close it appears to losing coherence. Its outer layers are not tightly bound. They exist in a state where gravity barely maintains control, and where even small fluctuations in radiation pressure can send material drifting outward into space. This is not a star sealed neatly into a sphere, but a vast breathing structure whose boundaries constantly fluctuate. In such stars, the concept of a surface becomes misleading. There is no sharp transition from star to space. Instead, density and temperature taper gradually, fading outward over distances so large that defining an edge becomes an act of interpretation rather than observation. In practical terms, this means Stephenson 2.18 does not end, it thins. This thinning creates a strange paradox. The star is enormous, yet parts of it are barely there. Its size comes not from concentration, but from extension. Matter is spread thin across a colossal volume, making the star fragile in a way compact stars are not. The larger it becomes, the harder it is to keep itself together. This fragility plays a central role in the star's destiny. Massive stars are destined to die violently, but how they die depends on subtle balances between mass, rotation, and internal structure. In stars like Stephenson 2.18, these balances are precarious. The star's own size works against it, slowing internal communication between layers and complicating collapse. When the core of such a star finally fails, when fusion can no longer generate enough pressure to resist gravity, collapse begins from the inside. But unlike smaller stars, the collapse does not immediately affect the outer layers. Information travels at finite speed. Pressure changes propagate outward slowly. For a star of this scale, the outer regions may remain unaware of the core's collapse for hours. During that delay, the core implodes catastrophically, compressing matter to densities beyond imagination. What follows depends on conditions that are still poorly understood. In some scenarios, the collapse triggers a rebound that tears the star apart in a supernova, blasting the outer layers into space. In others, the core collapses directly into a black hole, swallowing much of the star with surprisingly little outward violence. Stephenson 218 may exist near the boundary between these outcomes. Its immense size and diffuse envelope complicate the traditional supernova mechanism. Energy released at the core may dissipate before reaching the outer layers effectively. The star's own scale could dampen the explosion, allowing much of the material to fall inward rather than being expelled. This possibility challenges a deeply ingrained image of massive stars ending their lives in spectacular explosions. For the largest stars, death may be quieter than expected, not gentle but contained. A collapse that removes a star from the universe without announcing itself across galaxies. Even if a supernova does occur, its structure would differ from familiar examples. The explosion would take longer to unfold. Shockwaves would travel vast distances through tenuous material. The visual signature would be stretched in time and space. What observers might see would not be a sudden flash, but a prolonged transformation. What makes this particularly fascinating is that Stephenson 218's death, however it occurs, will reshape its surroundings. The material it sheds or expels will enrich the interstellar medium with heavy elements forged in its interior. These elements are essential for the formation of planets, moons, and eventually life. In this sense, the star's instability is not wasteful, it is productive. Yet the scale of that productivity is difficult to grasp. The volume of material involved is enormous. The energy exchanged is vast. The region of space affected could span many light years. Stephenson 218 is not just a single event waiting to happen. It is a future influence extending far beyond itself. This influence highlights a deeper truth about the universe. Extremes are not anomalies to be corrected. They are experiments. The cosmos runs naturally. Given enough mass and time, matter will explore configurations that seem excessive, inefficient, or unstable. The universe does not optimize for elegance. It allows abundance, redundancy, and excess. Stephenson 218 exists because nothing forbids it. That absence of prohibition is more unsettling than any dramatic explanation. There is no cosmic rulebook stating that stars must remain within comfortable limits. The laws of physics permit enormous inflation, even when it leads to instability. Balance is temporary. Extremes are allowed. This realization reframes how we think about cosmic order. The universe is not carefully tuned to avoid extremes. It is tuned to allow them until they collapse under their own weight. Stability is not the goal. Exploration is. In that sense, Stephenson 218 is not an exception. It is a manifestation of the universe testing its own boundaries, a reminder that physical law does not seek moderation. This also changes how we think about rarity. Rare objects are not necessarily mistakes. They are often indicators of processes operating at the edge of parameter space. Stephenson 218 tells us that stellar evolution does not end neatly at Betelgeuse-sized stars. It continues into regimes where intuition fails. The star's obscured location adds another layer of complexity. Hidden behind dust, it exists almost unseen, known primarily through indirect measurements. Its presence suggests there may be other extreme stars we have not yet identified, lurking behind dense clouds, quietly challenging our understanding. This possibility unsettles the sense of completeness we sometimes feel about astronomical catalogues. The universe may contain structures even larger, even more diffuse, and even more unstable than Stephenson 218, simply waiting for the right instruments to reveal them. At this point, the star begins to feel less like a singular curiosity and more like a threshold, a marker indicating where stars transition from objects into environments, where structure becomes so large that it blurs into space itself. Stephenson 218 is not just a record holder, It is a question made of matter, a question about how far scale can stretch before identity collapses. And as we move forward, that question will deepen, because beyond its physical behavior lies a more subtle challenge, not about what the star is, but about how the human mind copes with realities that no longer fit into the frameworks it evolved to use. Stephenson 2:18 does not merely exist at the edge of stellar physics. It exists at the edge of comprehension, and the closer we look, the more that edge begins to feel less like a boundary and more like an invitation to rethink what size really means in a universe that does not care how comfortable understanding feels. As the picture grows larger, Stephenson 2:18 begins to reshape not only stellar theory, but the way scale itself is handled in astronomy. The star forces a confrontation with a quiet assumption that often goes unspoken, that the universe, no matter how vast, will still organize itself into sizes that remain conceptually manageable. Stephenson 2:18 challenges that assumption by existing comfortably outside the range where intuition remains reliable. One of the first things this star disrupts is the idea that there is a natural upper limit to how large a star can appear while still functioning as a star. Traditional models suggest that radiation pressure, mass loss, and instability should prevent stars from inflating beyond certain thresholds. Yet here is an object that appears to sit right at, or possibly beyond, those thresholds without immediately tearing itself apart. This does not mean the models are wrong, but it does mean they are incomplete. The incompleteness comes from complexity. Stellar models often rely on simplifications that work well for most stars but struggle at extremes. They assume relatively smooth interiors, well-defined boundaries, and predictable feedback between layers. Stephenson 2:18 violates each of these assumptions in subtle ways. Its interior is turbulent, its atmosphere is extended and porous, its feedback mechanisms operate across distances so vast that delays become significant. Inside the star, cause and effect are separated by space. A change near the core does not instantly influence the outer layers. Energy, pressure, and motion take time to propagate. This creates lag, overshoot, and oscillation. The star does not respond as a single unit. It behaves more like a loosely coordinated system of regions, each operating on its own timescale. This internal delay is one reason such stars can inflate to such extremes. The core may already be transitioning toward collapse, while the outer layers continue expanding, unaware of what is coming. The star, in a sense, outruns its own stability. By the time the consequences catch up, the expansion has already gone too far to reverse easily. Another disruptive factor is rotation. Massive stars often rotate rapidly, and rotation alters how gravity acts across the star. Centrifugal forces reduce effective gravity near the equator, allowing material to lift outward more easily. In a star as large as Stephenson 2:18, even modest rotation can have dramatic effects on shape and stability, subtly flattening the star and redistributing mass. This redistribution further complicates attempts to define a single radius. The star may not be spherical in the way smaller stars are. Its outer envelope could bulge unevenly, with regions extending farther out than others. From some angles, the star might appear larger than from others. This alone introduces uncertainty into size estimates and challenges the idea that size is a single, well-defined number. What emerges instead is a picture of a star that is not a clean object, but a dynamic region of influence. Stephenson 2:18 does not simply occupy space, it dominates it. The gas and dust surrounding it are not clearly separate. They are part of an extended system shaped by the star's gravity, radiation, and mass loss. The boundary between star and environment becomes ambiguous. This ambiguity forces astronomers to reconsider how stellar environments are defined. Is the material loosely bound to the star part of the star, or part of the interstellar medium? At what point does influence become ownership? These are not philosophical questions alone. They affect how mass, size, and evolution are calculated. Stephenson 1.8 also complicates ideas about stellar populations. If stars can reach such enormous sizes late in life, then catalogues of largest stars may be snapshots of a fleeting phase rather than a stable category. A star may only spend a brief fraction of its life in this inflated state. Catching it at the right moment requires both timing and the right observational tools. This raises the possibility that Stephenson 2.18 is not unique, but simply the most extreme example currently visible. Other stars may briefly reach similar sizes before collapsing or shedding enough mass to shrink again. If so, then the universe may produce these giants more often than we realize. But they are rarely observed because the window is narrow. That possibility subtly shifts how rarity is interpreted. Rare does not always mean unlikely. Sometimes it means short-lived. This has implications for how we think about the evolution of galaxies. Massive stars play a disproportionate role in shaping their environments. They enrich space with heavy elements, sculpt surrounding gas clouds, and influence star formation nearby. A star as large as Stephenson 2.18 would exert an enormous influence over its local region even before it dies. Its radiation, winds, and eventual collapse would inject energy and material into the surrounding cluster on a scale far beyond smaller stars. In this sense, the star is not just a passive object. It is an agent of change despite its apparent instability. Yet even here, scale complicates intuition. The star's energy output is spread over such a large surface area that its intensity per unit area is relatively low. Its influence is broad rather than sharp. It shapes its environment gently but persistently, like a slow-moving tide rather than a sudden storm. This gentle dominance aligns with a broader pattern in the universe. The largest structures often act slowly. They do not need violence to matter. Their scale alone ensures influence over long timescales. Stephenson 2.18 embodies this principle. It does not flare dramatically. It does not dominate visually. It reshapes space quietly, over time, by simply being as large as it is. This quiet influence is part of what makes the star so unsettling conceptually. It violates the expectation that extremes must announce themselves loudly. Instead, it hides behind dust, glowing softly in wavelengths our eyes cannot see, testing the limits of physics without spectacle. In doing so, it reminds us that the universe does not reserve its most extreme phenomena for moments of drama. Some of its greatest experiments unfold slowly, patiently, almost invisibly. As researchers refine models to accommodate objects like Stephenson 2.18, the star becomes more than a curiosity. It becomes a calibration point, a constraint. A reminder that any theory of stellar evolution must be flexible enough to handle not just typical cases but outliers that push every parameter to its edge. The star's existence encourages humility. It suggests that our current frameworks capture trends, not absolutes. That nature explores corners of possibility we have not yet fully charted. And perhaps most importantly, it reframes the idea of breaking scale. Stephenson 2.18 does not break scale by violating physics. It breaks scale by exposing the limits of our mental tools. The laws remain intact. What breaks is our ability to visualize, to compare, to intuit. The universe allows stars to grow so large that they stop feeling like stars at all. They become landscapes. And in confronting Stephenson 2.18, astronomy is forced to acknowledge that scale is not just a property of objects, it is a challenge imposed on understanding itself. As the implications of Stephenson 2.18 continue to unfold, the focus naturally shifts from theory to perspective. Not scientific perspective alone, but human perspective. Stars like this expose a gap between what mathematics can describe and what the mind can comfortably imagine. Equations may capture its radius, its mass loss, its luminosity, but none of those numbers prepare intuition for what such an object means in physical terms. When astronomers describe Stephenson 2, 1/8 as one of the largest known stars, the statement is technically accurate and yet deeply insufficient. Largest implies comparison, ranking, hierarchy, but hierarchy breaks down when differences become too extreme. At this scale, Stephenson 2.18 does not simply outrank other stars. It exits the category in which ranking remains meaningful. This is where scale becomes experiential rather than numerical. Imagine placing familiar objects inside this star, not as metaphors, but as spatial exercises. The orbit of Earth would vanish inside its interior without leaving a mark. Jupiter's orbit would dissolve into its diffuse atmosphere. Even Saturn's vast path would not define a boundary. What was once a system becomes a detail. What was once a distance becomes texture. In this environment, motion loses its usual reference points. Travelling through Stephenson 2.18 would not feel like approaching an object. It would feel like entering a region, one that continues without obvious change. There would be no clear moment when you could say you had arrived. The star would surround you gradually, imperceptibly, long before you could identify its presence. This gradualness is one of the most disturbing features of extreme scale. Humans are accustomed to edges, doors, horizons, boundaries that signal transition. Stephenson 2.18 has none that matter. Its density increases so slowly with depth that crossing from space into star would be less like entering a surface and more like losing the concept of outside altogether. This blurring erodes the mental distinction between object and environment. A star becomes something you inhabit rather than observe, something that contains space rather than occupies it. At this point, the language we use to describe stars begins to fail. Terms like surface, edge, and radius are conveniences, not realities. They are approximations imposed by measurement, not intrinsic features of the object. Stephenson 2.18 exposes those approximations as fragile. This fragility is not a flaw in science. It is a reminder of what science actually does. It builds models that work where they are needed most. When objects drift beyond those needs, the models must be rethought, not abandoned. Stephenson 2.18 has become one of those forcing cases. It compels astronomers to confront questions that are rarely asked outside of theory. How do we define an object whose influence fades gradually rather than stopping? How do we distinguish a star from its surrounding medium when the difference is one of degree rather than kind? At what point does a star stop being a star and start being a stellar environment? These questions are not merely semantic. They affect how mass is calculated, how energy transport is modelled, how stellar lifetimes are estimated. When the boundary is unclear, every dependent quantity inherits uncertainty. And yet, despite all this ambiguity, the star continues to obey the same physical laws as every other star. Gravity still pulls inward, radiation still pushes outward, fusion still converts mass into energy. Nothing exotic is required, no new physics is invoked. This is perhaps the most unsettling part. Stephenson 2.18 does not exist because the universe bent its rules. It exists because the rules, when followed honestly, allow extremes far beyond what intuition expects. The laws of physics are not tuned for comfort, they are tuned for consistency. Consistency does not guarantee moderation. The star's existence also reframes how we think about observation. Stephenson 2.1, it is not directly visible in most wavelengths. It reveals itself primarily through infrared light, penetrating the dust that hides it. This means our awareness of such extremes is deeply tied to technology. Without the right instruments, objects like this remain invisible, not because they are rare, but because they are hidden. This raises an uncomfortable possibility. The universe may contain many structures that challenge our assumptions, but we only encounter them when technology catches up. Our picture of reality is not wrong, it is incomplete, filtered by what we can currently detect. Stephenson 2.18 is a reminder of that limitation. It also challenges the idea that the universe reserves its most dramatic behaviour for violent events. There is nothing explosive about this star's current state. No jets, no flares, no bursts of radiation announcing its presence. Its extremity is static, slow and quiet. This quietness is deceptive. It makes the star easy to overlook, even though its implications are enormous. It is not spectacle that defines its importance, but scale. And scale, once it crosses certain thresholds, stops behaving intuitively. This realization has subtle psychological consequences. Humans evolved to navigate environments where scale differences were modest. Hills, oceans, storms, large by human standards but trivial by cosmic ones. The brain is not built to process objects that erase reference frames. Stephenson 2.1.8 does exactly that. It removes the frame. When scale collapses, meaning begins to drift. Words like big, far, and inside lose precision. The star becomes less an object of analysis and more a boundary case, a demonstration of where cognition meets its limits. This does not diminish scientific understanding, it deepens it. True understanding is not the elimination of mystery, it is the recognition of where mystery remains inevitable. Stephenson 2.1.8 marks such a place, not because it is unknowable, but because knowing it fully requires tools, conceptual and perceptual, that humans do not naturally possess. And yet, the universe does not care about those limitations. It produces objects like this casually, without intention or commentary. They exist whether or not they are comfortable to imagine. This indifference is not hostile, it is neutral. Stephenson 2.1.8 exists because the conditions allowed it to form, inflate, and persist for a brief window of cosmic time. It will disappear just as quietly, collapsing or exploding according to rules that do not pause to accommodate comprehension. The star does not ask to be understood. It does not signal its importance. It simply exists at a scale where understanding becomes strained. As we move forward, the significance of Stephenson 2.1.8 shifts again, not toward its future fate, but toward what it reveals about the universe's tolerance for extremes. Because if a single star can grow so large that it becomes an environment rather than an object, then scale itself is not a ladder with rungs, it is a slope, and somewhere along that slope, the mind loses its footing, not because it has failed, but because the ground itself no longer behaves the way intuition expects. Stephenson 2.1.8 occupies that place, not as a spectacle, but as a quiet reminder that the universe is far less constrained by imagination than we are. As the exploration deepens, Stephenson 2.1.8 begins to feel less like an extreme example and more like a lens through which the universe reveals how it treats excess. Not excess in the moral sense, but excess in physical terms. Mass gathered too quickly, energy released too unevenly, structure stretched beyond the scale where coherence feels natural. This star exists where abundance itself becomes unstable. In most astrophysical systems, limits emerge organically. Planets cannot grow indefinitely because gravity compresses them into different states of matter. Stars cannot burn forever because fuel runs out. Galaxies cannot collapse completely because angular momentum resists it. These limits give the universe a sense of order. Stephenson 2.1.8 unsettles that sense because it appears to approach a limit without clearly crossing it. The star seems to hover at a boundary where two futures compete. One future pulls inward, toward collapse and simplification. The other pushes outward, toward dispersion and dissolution. Neither has fully won. The star remains suspended between them, massive yet diffuse, luminous yet cool, coherent yet fraying. This suspension is not static, it is dynamic, in slow motion. Every moment the star negotiates its own existence. Energy generated deep within the core struggles to reach the surface. Radiation pressure pushes outward while gravity resists. Pulsations ripple through layers separated by distances that dwarf planetary systems. The star does not settle, it endures. This endurance challenges a subtle assumption in astronomy, that stability implies longevity. Stephenson 2.18 is not long-lived in the cosmic sense. Its current state is brief, measured against the age of the galaxy. Yet while it exists, it appears remarkably persistent. It does not tear itself apart immediately. It does not collapse the moment instability arises. Instead, it stretches time, lingering in a condition that feels unsustainable yet continues. This tension exposes an important truth. Stability in physics is not binary. It is not simply stable or unstable. There are gradients, thresholds, and metastable states, configurations that can exist for long periods even though they are not truly secure. Stephenson 2.18 inhabits one of these states. It is balanced but precariously. Understanding this helps explain why such stars are rare without being impossible. The universe allows them but does not preserve them. They arise briefly, then disappear, leaving behind consequences rather than continuations. Their rarity is a result of timing, not prohibition. This perspective reframes the idea of breaking scale. Stephenson 2.18 does not break scale by exceeding a rule. It breaks scale by occupying a state that physics permits but does not favour for long. The star is a temporary victory of expansion over collapse, a momentary dominance of outward pressure over gravity. In this way, Stephenson 2.18 becomes a reminder that the universe does not enforce moderation, it enforces consistency. If the equations allow something to exist, it will exist, at least briefly. There is no preference for elegance, symmetry, or convenience. This indifference extends to formation as well. The star did not form because it was needed or because it served a purpose. It formed because enough mass gathered in one place quickly enough under conditions that allowed runaway growth. Star formation is not a careful process. It is opportunistic. Regions with excess gas collapse rapidly, producing massive stars before feedback can regulate them. Stephenson 2.18 is likely the product of such a runaway event. A dense cluster, rich in material, formed stars so massive that regulation arrived too late. By the time radiation and winds began to clear surrounding gas, the star had already reached extraordinary size. What followed was not correction, but adaptation. The star adjusted to its own excess rather than undoing it. This adaptation is visible in its mass loss. Instead of exploding prematurely, the star sheds material gradually. It leaks, it exhales. It distributes its excess into space rather than releasing it all at once. This behavior is not planned. It is emergent. It arises because the star cannot contain everything it has become. There is something quietly profound in this. At extreme scales, containment becomes impossible. Objects grow not by accumulating indefinitely, but by constantly losing parts of themselves. Stephenson 2.18 exists not as a sealed entity, but as a flowing one. Its boundaries are defined by exchange, not isolation. This makes the star less like a monument and more like a process unfolding across distances so large that our usual categories struggle to follow. When we call it a star, we are naming the densest region of a much larger phenomenon. This view aligns with a broader pattern in the universe. The largest structures are rarely rigid. Galaxies are not solid objects. They are rotating systems of stars, gas, and dark matter. Clusters of galaxies are even more diffuse. Stephenson 2.18 fits this hierarchy. As size increases, solidity gives way to fluidity. Yet unlike galaxies, Stephenson 2.18 remains governed by stellar physics. Fusion still powers it, gravity still binds it. This overlap, stellar processes operating at near-galactic scales, makes the star particularly unsettling. It exists in a hybrid regime where familiar rules apply in unfamiliar ways. This hybridity also complicates intuition about causality. Changes inside the star do not propagate instantly. Information moves at finite speed. Pressure waves travel slowly through extended layers. This means that different parts of the star can exist in different moments of its evolution simultaneously. The core may be approaching collapse while the outer layers behave as if expansion is still appropriate. Time within such a star becomes layered. This layered time challenges the idea that an object has a single state at any given moment. Stephenson 2.18 does not have one condition. It has many, distributed across space. Understanding it requires abandoning the notion that objects must be uniform in time as well as space. The star's eventual fate will resolve this complexity brutally. Collapse, explosion, or disappearance will impose unity again. But until then, the star exists as a distributed negotiation between competing processes. This negotiation is not visible to the naked eye. It is inferred through spectra, models, and indirect measurement. Much of what we know about Stephenson 2.18 is probabilistic. There are margins of error, alternative interpretations, unresolved debates. The star resists being pinned down. That resistance is not a failure of observation, it is a feature of extremes. At the edges of parameter space, uncertainty grows. Definitions blur. Precision becomes conditional. Stephenson 2.18 teaches this lesson without spectacle. It does not overwhelm with brightness or violence. It overwhelms quietly by refusing to fit neatly into the boxes we built for stars. And perhaps that is its deepest significance. The star reminds us that the universe does not scale smoothly with our expectations. It leaps, it stretches, it tolerates forms that feel excessive simply because nothing forbids them. In doing so, it exposes a subtle truth. Scale is not a ladder with predictable steps. It is a landscape with cliffs, plateaus, and valleys. Stephenson 2.18 stands on one of those plateaus, a place where size, stability, and identity blur into something that feels less like an object and more like a condition that exists briefly, quietly, and without apology. And in acknowledging that, astronomy takes another step toward understanding not just what the universe contains, but how indifferent it is to the limits of human imagination. As Stephenson 2.18 continues to challenge the frameworks we rely on, its role subtly shifts from subject to reference point. It becomes a measuring stick not for size alone, but for how far physical systems can be stretched before familiar concepts dissolve. The star no longer feels like an anomaly to be explained away. It begins to feel like a boundary condition, an example of how the universe behaves when pushed to the edge of what stability can tolerate. One of the most revealing aspects of Stephenson 2.18 is how it reframes the relationship between mass and influence. In everyday thinking, more mass implies stronger gravity, tighter binding, and greater control over surroundings. Yet in this star, immense mass coexists with remarkable looseness. Its outer layers are so weakly bound that influence becomes diffuse. Gravity still rules, but it rules gently, across enormous distances. This gentleness alters how the star interacts with its environment. Instead of carving sharp boundaries, it creates gradients. Gas is not violently expelled in narrow jets, but slowly carried outward by winds and pulsations. Dust does not crash into surrounding space, it drifts, forming extended shells and envelopes that blur into the interstellar medium. The star's presence is felt not as a forceful intrusion, but as a slow reshaping of space around it. In this way, Stephenson 2.18 behaves less like a point source and more like a region of influence. Its gravity, radiation, and mass loss extend outward gradually, merging with the background rather than standing apart from it. This behavior is unusual for stars, which are often treated as discrete entities interacting across empty space. Stephenson 2.18 challenges that simplification. The challenge becomes especially clear when considering feedback. In most stellar environments, feedback is decisive. Radiation and winds from massive stars clear surrounding gas, regulate further star formation, and impose order on chaotic regions. But in the case of Stephenson 2.18, feedback is spread thin. Its influence is broad but diluted, shaping space slowly rather than abruptly. This diluted feedback may explain why the star has not destroyed its own environment despite its size. By acting gently rather than explosively, it avoids triggering the kinds of instabilities that would rapidly dismantle it. Excess is released gradually, pressure is relieved through expansion and loss rather than collapse. There is a quiet efficiency in this inefficiency. By not concentrating its influence, the star prolongs its own existence. It remains unstable but not catastrophically so. This balance is not engineered, it is emergent, a consequence of scale itself. Scale alters everything. As systems grow larger, their internal communication slows. Signals take longer to travel, feedback loops stretch, overshoot becomes more likely. Stephenson 2.1.8 embodies this effect in stellar form. Its vast size introduces delays that allow processes to coexist that would otherwise cancel each other out quickly. This delay-driven coexistence is one reason the star appears so paradoxical. It should not exist in a simple static model. But when time delays are introduced, new behaviors emerge. Expansion can continue even as collapse begins elsewhere. Mass loss can stabilize growth even as gravity strengthens. The star becomes a system out of phase with itself. Out-of-phase systems are notoriously difficult to predict. Small changes can have disproportionate effects. Minor fluctuations can be amplified or dampened depending on timing and location. This makes Stephenson 2.1.8 inherently unpredictable, not because it violates physical law, but because it operates in a regime where sensitivity is high. This sensitivity adds another layer of uncertainty to its future. Will it shed enough mass to avoid a catastrophic collapse? Will it collapse directly into a black hole, bypassing a visible explosion? Will its outer layers drift away before the core can influence them? Each outcome is plausible, and small differences in initial conditions could determine which one occurs. The star does not announce which path it will take. It does not signal its intentions. It simply continues to exist, balancing forces that grow increasingly incompatible. This ongoing balance reframes the notion of largest. Size alone is not what makes Stephenson 2.1.8 remarkable. What makes it remarkable is that it remains coherent at such a size. Coherence, not scale, is the true achievement here. Coherence at extreme scale requires compromise. The star compromises density for volume. It compromises intensity for extent. It compromises stability for duration. Each trade-off allows existence to continue a little longer. These trade-offs are not unique to stars, they appear across the universe. Galaxies trade density for size. Clusters trade coherence for reach. Even the universe itself trades structure for expansion over time. Stephenson 2.1.8 fits naturally into this pattern. It is not an aberration. It is an expression of a general principle. Larger systems survive by becoming softer. Softness in this context does not mean weakness. It means flexibility, the ability to absorb change without shattering. The star's diffuse envelope absorbs internal fluctuations, smoothing them out over vast distances. This prevents localized instabilities from immediately cascading into collapse. Yet softness has limits. Eventually, gravity will overcome flexibility. The core will fail. When that happens, softness will no longer protect the star. Collapse will propagate outward, unifying the system in a way it has avoided for millions of years. Until then, the star remains in a liminal state, neither firmly stable nor actively dying. It occupies a middle ground that feels unnatural only because it lies outside everyday experience. This liminality has philosophical resonance. Stephenson 2.1.8 exists in a state of almost too much, almost too large, almost too unstable, almost too diffuse. It is an object that lives in the margin between possibility and impossibility. Margins are where understanding grows. By studying such stars, astronomers are forced to expand their frameworks. Models must account for delay, diffusion, and gradient-based influence. Definitions must soften. Certainty must give way to ranges and probabilities. Stephenson 2.1.8 1-8 teaches science to be less rigid. It also teaches patience. The star does not offer immediate answers. Its evolution unfolds slowly, subtly, across timescales far beyond observation. We infer its behavior from snapshots, indirect signals, and simulations. Much of what we say about it is provisional. This provisional nature is not a weakness. It is an honest reflection of how knowledge works at extremes. The farther we push into unfamiliar regimes, the more humility is required. Stephenson 2:18 invites that humility simply by existing, and in doing so, it quietly shifts the narrative of cosmic scale. The universe is not just a collection of objects separated by distance. It is a continuum of influence, softness, and compromise. Size does not guarantee dominance, mass does not guarantee control, extremes do not guarantee spectacle. Sometimes the most extreme objects are defined not by what they do, but by how gently they do it. Stephenson 2:18 does not roar, it breathes, slowly, expansively, at a scale that turns distance into texture and time into a background condition. And in that breathing it reveals a universe that tolerates excess not by resisting it but by letting it diffuse until collapse becomes inevitable, not as a failure, but as a completion. The star stands as a reminder that scale, once pushed far enough, transforms behavior itself. Objects stop acting like objects. Processes stop acting like events. And existence becomes something that unfolds quietly, across distances too large to feel and times too long to witness. Stephenson 2:18 exists in that quiet unfolding, not to be admired for its size alone, but to be recognized as a place where scale ceases to behave the way we expect and begins to teach us something deeper about how the universe endures its own extremes. As Stephenson 2:18 settles into its role as a lesson rather than a spectacle, its greatest contribution may lie in how it reframes the idea of limits. Limits are often imagined as hard barriers, points where something simply cannot exist, but the universe rarely works that way. Instead, it allows systems to approach limits asymptotically, lingering near them in unstable balance before eventually drifting away or collapsing inward. Stephenson 2:18 occupies one of those lingering zones where the boundary between allowed and unsustainable becomes stretched thin. This stretched boundary changes how astronomers think about inevitability. In simpler systems, outcomes feel predictable. A star of a certain mass will follow a certain evolutionary path. Fuel runs out, gravity wins, and the sequence unfolds. But Stephenson 2:18 exists in a regime where multiple futures remain open simultaneously. Its present state does not point cleanly toward a single destiny. Instead, it fans out into possibilities that differ not by dramatic physics, but by subtle timing. Timing becomes everything at this scale. When processes unfold over distances measured in billions of kilometers, synchronization breaks down. Energy production in the core, pressure waves in the envelope, and mass loss at the outskirts no longer act in concert, they slip past one another, interacting imperfectly. The star's future becomes sensitive to which process gains even a slight advantage first. This sensitivity means that Stephenson 2:18's eventual fate may depend on details we cannot currently resolve. Slight differences in rotation rate, metallicity, or internal mixing could determine whether it ends its life in a visible explosion, a muted collapse, or a gradual dispersal followed by a quiet disappearance. The star does not advertise which path it will take. It keeps all options open until the last moment. This uncertainty challenges a deep-seated human desire for narrative closure. We prefer stories with clear beginnings, middles, and ends, but Stephenson 2:18 resists that structure. Its story is not a clean arc, it is a plateau, a prolonged state of tension where nothing decisive happens, even though everything is poised to change. In this way, the star mirrors a broader truth about the universe. Many of the most important transitions do not occur in moments of drama, but in long stretches of near equilibrium. Galaxies drift for billions of years before merging. Planetary systems settle slowly. Even the universe itself spends far more time coasting than transforming. Stephenson 2.1.8 fits this pattern. Its extremity is not explosive, it is extended. This extension has consequences for how we interpret observation. Astronomical data often capture moments frozen in time. We see the star as it was when the light left it, and we interpret that snapshot as a representative state. But for a star like Stephenson 2.1.8, no single snapshot is truly representative. Its structure is in constant flux, oscillating subtly across vast regions. Any image or spectrum captures only one configuration among many. This realization complicates classification. Is Stephenson 2.1.8 a red supergiant, a hypergiant, a transitional object? Each label captures part of the truth and misses the rest. The star does not fit neatly into a box because it occupies a continuum between categories. Its properties overlap multiple definitions without fully satisfying any of them. This overlap exposes the artificial nature of many astronomical categories. They are tools, not truths. They help organize understanding, but they do not define reality. Stephenson 2.1.8 reminds us that nature does not consult our taxonomies before producing objects. The star's existence also raises questions about how common such boundary objects might be. If Stephenson 2.1.8 exists now, it implies that the processes capable of producing it are not unique. They may be rare, but rarity does not imply singularity. The universe is vast, and even rare processes can occur many times across its expanse. Yet detection remains a challenge. Objects like Stephenson 2.1.8 often hide behind dust and distance, visible only in specific wavelengths. They may be underrepresented in catalogues not because they are uncommon, but because they are difficult to observe. As observational tools improve, more such stars may come into view, quietly reshaping our sense of what is typical. This possibility has a humbling implication. Our current picture of stellar evolution may be biased toward objects that are easy to detect and classify. Extreme, diffuse, or obscured stars may be systematically undercounted. Stephenson 2.1.8 may be a hint of a hidden population rather than an isolated marvel. If so, then the universe's capacity for scale may be broader than we currently appreciate. The upper end of stellar size may not be defined by one record holder, but by a fuzzy range populated by transient giants that appear and vanish without fanfare. This fuzziness challenges the idea of cosmic records altogether. Records imply permanence and clarity, but in a universe governed by change, records are provisional. Today's largest star may be surpassed tomorrow, or may shrink, collapse, or fade from view before a challenger is even recognized. Stephenson 2.1.8's significance, then, is not that it holds a title. It is that it demonstrates how meaningless such titles become at extremes. When objects approach the limits of stability, comparison loses value. What matters is not who is biggest, but what the existence of such size reveals. And what it reveals is this: the universe tolerates imbalance for surprisingly long periods. It allows systems to hover near failure without immediately resolving them. It does not rush toward equilibrium. It permits tension to persist. This tolerance has profound implications beyond stars. It suggests that the universe is not optimized for efficiency or simplicity. It is optimized for continuity. As long as nothing violates fundamental conservation laws, systems are allowed to exist in awkward, stretched, and inefficient states. Stephenson 2.1.8 embodies this allowance. It is not an elegant solution. It is a compromise made of matter and energy stretched thin across a volume that barely holds together. And yet, that compromise works. Temporarily. This temporary success invites a subtle shift in how we think about cosmic failure. Collapse is not necessarily a failure of a system. It is often the completion of a process that could not continue indefinitely. Stephenson 2.18's eventual end will not represent a breakdown of physics, but its fulfillment. Until that moment arrives, the star remains suspended in a state that feels unresolved. It exists not as an answer, but as an ongoing question. A question about how far scale can be pushed before identity dissolves. A question about how long imbalance can persist before resolution becomes unavoidable. The universe does not rush to answer that question. It allows it to linger, stretched across time and space. And in that lingering, Stephenson 2.18 teaches a lesson that extends far beyond stellar astronomy, that the most revealing phenomena are often not those that change suddenly, but those that endure quietly at the edge of what seems possible. The star does not shout its importance. It simply remains vast, diffuse, and unresolved, inviting us to reconsider what we mean when we talk about limits, stability, and scale in a universe that rarely draws clear lines. In the presence of Stephenson 2.18, certainty gives way to patience, and patience in turn opens space for a deeper understanding of how the universe accommodates extremes, not by correcting them immediately, but by letting them exist long enough to teach us something new. As the understanding of Stephenson 2.18 continues to mature, its importance begins to shift once again, this time away from what it is, and toward what it reveals about the universe's attitude towards scale itself. The star does not merely occupy an extreme position on a chart, it exposes a deeper principle, that the universe does not enforce proportion. There is no rule requiring systems to remain comfortably scaled to one another. If conditions allow excess, excess is permitted. This principle becomes especially clear when Stephenson 2.18 is placed alongside more familiar stars. Our Sun, for example, feels substantial because it dominates its local environment. It governs planetary orbits, defines a habitable zone, and provides energy in a tightly controlled way. Its size, mass, and influence feel balanced. Stephenson 2.18, by contrast, feels unbalanced not because it violates physics, but because it exceeds the scale at which balance remains intuitive. The star's vastness stretches cause and effect relationships. Actions taken in one region do not immediately influence others. Feedback loops slow down. Regulation weakens. In smaller stars, instability is corrected quickly. Expansion triggers mass loss. Contraction increases temperature and pressure. Equilibrium is restored efficiently. In Stephenson 2.18, correction is delayed. By the time a response arrives, the condition it was meant to correct may have already evolved. This delay introduces a kind of cosmic inertia. The star continues in whatever direction it is already moving, not because it is stable, but because the mechanisms that would stop it cannot act fast enough across such distances. Expansion persists because gravity's response is slow. Mass loss continues because radiation pressure remains effective over extended regions. The star's behavior becomes less about balance and more about momentum. Momentum at this scale is not motion through space, but persistence through state. Stephenson 2.18 remains large because becoming smaller requires coordination across regions too vast to synchronize easily. Shrinking is not a single act. It would require the entire star to respond coherently. That coherence is precisely what extreme scale undermines. This insight reframes how astronomers think about runaway phenomena. Runaway processes are often imagined as rapid, explosive events, but Stephenson 2.18 demonstrates that runaway behavior can be slow. Growth can continue quietly, not because it is unchecked, but because the checks operate too diffusely to dominate. The star's size also complicates the idea of internal structure. In many stars, layers are well defined: core, radiative zone, convective zone, atmosphere. These regions interact strongly and predictably. In Stephenson 2.18, boundaries blur, layers overlap. convection cells may span distances larger than entire planetary systems. The star's interior becomes a landscape rather than a layered machine. This landscape-like interior challenges the assumption that stellar interiors are homogeneous on large scales. Instead, they may contain long-lived asymmetries, vast circulating flows, and localized instabilities that never fully cancel out. The star may not behave the same way in all directions at all times. It may wobble, pulse, and breathe unevenly. Such behavior would be invisible in smaller stars, where differences average out quickly. In Stephenson 2.1.8, they persist. The star's immense size allows imperfections to survive. It is not smooth, it is textured. Texture at this scale changes how we think about stellar identity. When an object becomes so large that different regions behave semi-independently, the idea of a single unified self begins to erode. The star is still one object in a gravitational sense, but functionally, it behaves like a collection of interacting regions rather than a single coherent unit. This does not mean the star is fragmented. It means that unity becomes statistical rather than absolute. The star holds together on average, over time rather than at every moment and location. Its coherence is emergent, not enforced. This concept mirrors how other large systems behave. Galaxies are unified by gravity, but individual stars follow their own orbits. Weather systems on planets are unified by atmosphere, but storms evolve independently. Stephenson 2.1.8 sits at a similar threshold within stellar physics. It is large enough for internal diversity to matter. Recognizing this helps explain why modeling such stars is so difficult. Simplified models assume symmetry and uniformity. They assume that deviations are small and transient. In Stephenson 2.1.8, deviations may be large and persistent. A model that averages them out may miss essential behavior. This does not invalidate modeling, it demands refinement. It pushes theory toward higher dimensionality, incorporating time delays, spatial gradients, and stochastic processes. Stephenson 2.1.8 becomes a test case for how far stellar theory can be extended before it must be fundamentally rethought. The star's quiet persistence also challenges the human tendency to associate importance with visibility. Stephenson 2.1.8 is not easily seen. It does not blaze brightly in the night sky. It hides behind dust, glowing softly in wavelengths our eyes cannot detect. Its influence is subtle, its presence inferred rather than obvious. Yet its implications are profound. This disconnect between visibility and significance is a recurring theme in astronomy. Many of the most important structures in the universe, dark matter halos, cosmic filaments, diffuse gas, are invisible directly. Stephenson 2.1.8 belongs to this category of quietly consequential objects. It also serves as a reminder that extremity does not always announce itself. Some of the universe's most radical experiments unfold slowly, quietly, and without spectacle. They challenge understanding not by overwhelming the senses, but by exceeding the limits of conceptual comfort. As attention lingers on Stephenson 2.4.4.1.8, a subtle shift occurs in how scale is perceived. The star stops feeling like something that must be explained away as an exception. Instead, it feels like a natural outcome of a universe that does not prioritize neatness. The universe allows systems to grow until they encounter constraints. Those constraints may not be sharp, they may be gradual, probabilistic, and delayed. Stephenson 2.1.8 exists in the space between allowance and constraint. It is permitted but not favoured. This distinction matters. Being permitted means existence is possible. Being favoured means existence is stable. Stephenson 2.1.8 demonstrates that the universe does not require both. It allows objects to exist even when they are fundamentally temporary. In that sense, the star is not a failure of regulation. It is a success of permissiveness. The universe is generous with possibilities, even when those possibilities lead to instability. This generosity has consequences. It ensures diversity, it allows exploration of parameter space, It produces objects that stretch understanding and force theory to adapt. Stephenson too regards 1/8 is one such product. As this understanding settles in, the star's role becomes clear. It is not merely an object to be measured. It is a boundary case that teaches by existing. It shows how far stellar physics can be pushed without breaking, and where breaking becomes inevitable. The star does not answer questions directly, it reframes them. Instead of asking how big a star can be, it encourages asking how long imbalance can persist. Instead of asking where boundaries lie, it encourages asking how boundaries blur. Instead of asking what is stable, it encourages asking what is allowed. These questions do not have simple answers. They unfold slowly, much like the star itself. Stephenson too, 1/8 remains suspended in that unfolding, vast, quiet and unresolved. Not as a spectacle, but as a demonstration of a universe that does not rush to impose order, that tolerates excess without apology, and that allows scale to stretch far beyond the comfort of imagination. In the presence of such an object, certainty feels premature, understanding becomes provisional, and the universe reveals itself not as a system of tidy limits, but as a landscape where extremes are not errors, but expressions of possibility. Stephenson too, 1/8 stands within that landscape, not as the end of scale, but as a signpost marking where scale stops feeling intuitive and begins demanding patience, humility, and a willingness to let go of familiar frames. It does not need to be the largest forever. It only needs to exist long enough to change how size itself is understood. As the final layers of understanding settle around Stephenson 218, the star's significance begins to crystallize in a quieter, more reflective way, not as a challenge to physics, not as a spectacle of excess, but as a demonstration of how the universe behaves when it is under no obligation to remain interpretable. The star's true impact lies in how completely it dissolves the expectation that nature should scale itself to human comprehension. At some point in confronting an object like Stephenson 218, the mind stops trying to visualize it accurately. Visualization gives way to acceptance. The star is no longer something to be pictured, but something to be acknowledged, a fact about reality that exists independently of mental imagery. This transition is subtle but important. It marks the boundary where understanding shifts from imagination to abstraction. This is not a failure of comprehension, it is an evolution of it. Much of science begins with analogy and metaphor. We compare stars to furnaces, galaxies to cities, space to oceans. These metaphors work because they translate unfamiliar scales into familiar ones. But Stephenson 218 resists translation. No familiar object behaves like it. No everyday experience maps cleanly onto it. The metaphors collapse under their own inadequacy. What remains is structure without imagery, relationships without pictures, numbers without intuition. And this is where Stephenson 218 becomes philosophically important. The star reminds us that reality is not obligated to be intuitive. The universe does not adapt itself to cognitive comfort. It produces structures according to physical law, not narrative coherence. If those structures exceed our capacity to imagine them, that is not a flaw in reality. It is a limit of perception. This realization echoes across scientific history. Atoms were once unimaginable. Curved space-time defied intuition. Quantum mechanics still resists visualization. In each case, understanding advanced not by forcing intuition to adapt, but by allowing abstraction to replace it. Stephenson 218 belongs to this lineage of concepts that require surrendering imagery in favor of relationship. The star is known not by what it looks like, but by how it behaves. Its temperature, luminosity, spectral lines, and mass loss rates tell its story. These quantities do not paint a picture, they define a pattern, and the pattern reveals something essential. That scale alters not just magnitude, but behavior. At sufficient size, systems stop responding proportionally. They respond qualitatively differently. feedback slows, boundaries blur, identity weakens. Stephenson 2.18 exists in this qualitative shift. This shift has implications beyond stellar astronomy. It suggests that whenever systems become large enough, whether stars, ecosystems, economies, or even civilizations, new behaviors emerge that cannot be predicted simply by scaling up smaller models. Complexity does not grow linearly with size. It changes character. In this sense, Stephenson 2.18 is a reminder that extrapolation has limits. What works for the Sun does not necessarily work for a star thousands of times larger. What works for ordinary stars does not automatically apply at the extreme end of the spectrum. Nature does not promise continuity of intuition. The star also reframes the idea of breaking scale. It does not break scale by surpassing a maximum. It breaks scale by making the very idea of a maximum feel misplaced. There is no sharp cutoff where stars suddenly cannot exist. There is only a gradual increase in instability, uncertainty, and impermanence. This gradualism is a recurring theme in the universe. Black holes do not form at a single mass threshold. Galaxies do not suddenly become clusters. Transitions are fuzzy, categories overlap. Stephenson 2.18 lives in one of these overlaps, where labels lose precision. In that overlap, the star becomes less a thing and more a condition where stellar physics stretches thin, where cohesion persists just long enough to matter, and where the difference between object and environment becomes ambiguous. This ambiguity invites a different kind of respect, not admiration for size alone, but appreciation for endurance. Stephenson 2.18 is not impressive because it is big. It is impressive because it continues to exist at all. Existence at that scale is non-trivial. It requires a delicate balance between forces that are no longer well matched. It requires time delays, gradients, and inefficiencies to align just enough to prevent immediate collapse. The star survives not because it is strong, but because the universe allows weakness to persist. This allowance challenges a deeply ingrained assumption that the universe favors robustness. In reality, it often tolerates fragility. It permits systems to exist in precarious states for extended periods, as long as nothing fundamentally forbids them. Stephenson 2.18 is fragile in the cosmic sense. It is not destined to last long. But fragility does not mean insignificance. Short-lived phenomena can reshape environments, challenge theory, and expand understanding. The star's fragility also carries a quiet emotional weight. There is something profoundly humbling about knowing that such an enormous object is temporary, that something capable of containing planetary orbits within its body is still fleeting on cosmic timescales. This humbling perspective dissolves anthropocentric hierarchies. Size does not guarantee permanence. Power does not guarantee survival. The universe does not reward magnitude with longevity. In this light, Stephenson 2.18 becomes a reminder of proportionality's illusion. What feels large to us is not necessarily enduring. What endures is not necessarily grand. Time, not size, is the ultimate arbiter. As attention drifts toward the star's eventual disappearance, its role in the cosmic story becomes clearer. It is not a culmination, it is a transition. It will leave behind enriched material, altered surroundings, and perhaps a compact remnant, but the star itself will not remain. And that is enough. Its purpose, if the word can even be used, is not to persist indefinitely. It is to exist long enough to expand the range of what we consider possible, to demonstrate that the universe can produce objects that stretch every comfortable boundary without tearing reality apart. Once that demonstration is complete, the star will fade from relevance, not because it failed, but because it fulfilled its role. This perspective reframes how extremes are valued. Extremes are not endpoints, they are explorations. Temporary excursions into regions of possibility that inform the whole by their brief presence. Stephenson 2.18 explored the upper reaches of stellar scale. It showed how far matter could inflate before cohesion thinned too much to sustain itself. It revealed how gently a system could hold together even as it approached collapse, and in doing so, it left behind something more durable than itself: insight. Insight into how the universe tolerates excess. Insight into how scale reshapes behavior. Insight into how understanding must evolve when intuition fails. The star does not need to survive to matter. It only needs to exist long enough to be noticed. In the quiet persistence of Stephenson 2:18, the universe demonstrates one of its most subtle lessons: that meaning is not always found in permanence, and that the most important boundaries are not those that cannot be crossed, but those that reveal how much must change once they are approached. Stephenson 2:18 stands at one of those boundaries, not as a warning, but as a spectacle, but as a quiet confirmation that reality is larger, softer, and less obligated to clarity than we often assume. And in recognizing that, understanding grows, not by conquering the extreme, but by learning how to coexist with what cannot be fully imagined. As the perspective widens one final time, Stephenson 2:18 stops feeling like a singular object and begins to feel like a mirror. Not a mirror that reflects the universe back at us, but one that reflects the limits of how we approach understanding itself. By existing so far outside familiar scale, the star exposes the quiet assumptions we bring into every act of explanation, assumptions about proportion, coherence, and the expectation that reality should remain narratively tidy. At first, the impulse when encountering an extreme object is to tame it with comparison. We say it could swallow the orbits of planets. We say light would take hours to cross it. We stack analogies until they collapse under their own weight. These comparisons are not wrong, but they are scaffolding. They help us approach the idea, not inhabit it. Eventually, the scaffolding must be removed, and what remains is the recognition that some scales cannot be domesticated by metaphor. Stephenson 2:18 exists in that undomesticated zone. This realization subtly shifts the role of astronomy. The field is often framed as a project of mapping, classifying and cataloguing, of turning the universe into a structured inventory. But objects like Stephenson 2:18 resist being neatly inventoried. They blur categories instead of fitting them. They stretch definitions until the definitions themselves become unstable. This does not weaken science, it strengthens it. Science advances not only by explaining what fits existing frameworks, but by encountering what forces those frameworks to bend. Stephenson 2:18 bends stellar theory not by contradiction, but by extension. It asks what happens when rules are followed faithfully into regimes where intuition no longer applies. And the answer is not chaos. The answer is subtlety. The star does not violate conservation laws. It does not require exotic physics. It simply inhabits a region of parameter space where familiar behaviors become slow, diffuse, and layered. Its extremity is not loud. It is quiet, persistent, and structurally awkward. This awkwardness is revealing. It shows that the universe is comfortable with inefficiency. It tolerates systems that are not optimized for clarity or longevity. As long as energy is conserved and forces balance on average, existence is permitted, even if it looks precarious from the outside. Stephenson 2:18 survives not because it is perfect, but because nothing has yet compelled it to resolve its tension. Collapse has not synchronized across its interior. Mass loss has not yet removed enough material to force contraction. The star lingers in a state of incomplete decision. This lingering has a temporal dimension that is easy to underestimate. On human timescales, the star appears static. On stellar timescales, it is fleeting. On cosmic timescales, it is almost instantaneous. Perspective determines meaning. Stephenson 2:18 teaches this lesson simply by existing long enough to be observed. It also reframes the idea of observation itself. Much of what we know about the star is inferred rather than seen. Its size is estimated, its structure modeled, its behavior reconstructed from limited signals filtered through dust and distance. There is uncertainty at every step, but that uncertainty is not ignorance, it is resolution. At extreme scale, certainty dissolves not because knowledge fails, but because precision loses relevance. When boundaries blur, exact numbers matter less than ranges. Behavior matters more than measurement. Stephenson 2.1.8 invites this shift from exactness to pattern recognition. Patterns, not particulars, are what endure. The pattern Stephenson 2.1.8 reveals is one of tolerance. The universe tolerates extremes. It tolerates imbalance. It tolerates objects that exist in states of near failure without immediately correcting them. This tolerance is not generosity, it is neutrality. The universe does not intervene unless intervention is forced by physical law. This neutrality carries a quiet implication. There is no cosmic quality control ensuring that objects remain understandable. There is no preference for elegance. There is only permission and consequence. Stephenson 2.1.8 exists because nothing forbade it. This idea can feel unsettling, especially to minds accustomed to seeking intention. We want the universe to produce extremes for a reason, to teach, to warn, to inspire. But the star does none of these things deliberately. Any meaning it carries is assigned, not embedded. And yet, meaning still emerges. Meaning emerges not from intention, but from contrast. Stephenson 2.1.8 matters because it contrasts with the stars we know. It expands the envelope of what we consider possible. It forces recalibration. In that recalibration, understanding grows. This growth is not linear. It does not arrive as a single insight. It accumulates slowly through discomfort, revision, and the abandonment of assumptions that no longer hold. Stephenson 2.1.8 accelerates this process simply by existing at a scale that resists simplification. It also encourages a different relationship with uncertainty. Instead of treating uncertainty as a temporary obstacle to be eliminated, the star frames it as an intrinsic feature of extreme regimes. Some questions cannot be answered with finality because the systems they refer to do not possess finality. Stephenson 2.1.8 is one such system. Its future is not fixed in detail. Its present is not uniform in structure. Its past is reconstructed rather than observed. And yet this does not diminish its reality. If anything, it makes the star more representative of the universe as a whole, a place where most things exist as processes rather than finished products. This process-oriented view dissolves the desire for definitive conclusions. There is no moment when Stephenson 2.1.8 becomes fully understood. Understanding remains provisional, contextual, and open-ended. Each improvement in observation adds detail, but also reveals new complexity. This openness is not a flaw, it is an invitation. It invites astronomy to move beyond static descriptions and toward dynamic narratives that accommodate change, delay, and uncertainty. It invites humility in the face of scale. It invites patience where intuition demands closure. Stephenson 2.1.8 also subtly reframes how significance is assigned. It is not important because it will change the fate of the universe. It is important because it reveals how little the universe cares about fitting into conceptual boxes. Its significance lies in what it destabilizes, not what it controls. The star does not dominate its galaxy, it does not anchor cosmic structure, it does not reshape space-time. And yet it matters deeply because it challenges the idea that importance must be tied to impact. Sometimes, importance lies in exposure of limits, exposure of assumptions, exposure of how far reality can stretch without breaking. Stephenson 2.1.8 exposes all three. As attention begins to drift away from the star itself, its influence persists in a subtler way. It lingers in models, in discussions, in the quiet recalibration of what astronomers consider reasonable. It becomes part of the background against which future discoveries are judged. When a new massive star is found, Stephenson 18 will be there, silently redefining what counts as surprising. When models predict upper bounds, it will be there, reminding theorists that bounds are often softer than they appear. In this sense, the star outlives itself conceptually. Long after it collapses or disperses, its challenge to scale will remain embedded in how stellar physics is approached. And that may be its most lasting contribution. Not a record, not a spectacle, but a gentle, persistent nudge toward intellectual flexibility. Stephenson, too. 18 teaches that understanding does not always arrive by narrowing focus. Sometimes it arrives by widening tolerance, by accepting that some phenomena exist at the edge of what can be cleanly described, and that this edge is not a failure point, but a frontier where curiosity must slow down, metaphors must be released, and certainty must soften. In standing at that frontier, Stephenson, too, 18 does not demand awe, it does not demand fear, it does not demand reverence. It simply asks for patience. Patience to sit with scale that cannot be pictured. Patience to accept systems that do not resolve neatly. Patience to let understanding remain unfinished. And in offering that lesson, quietly and without spectacle, Stephenson, too, 18 becomes more than the largest known star. It becomes a reminder that the universe is not obligated to make sense in ways that feel comfortable, only in ways that remain consistent with itself. Everything beyond that is an invitation to adapt. And Stephenson, too, 18, vast and diffuse, stands as one of the clearest invitations the cosmos has ever offered. As the exploration reaches its furthest edge, Stephenson, too, 18, begins to feel less like a subject of study and more like a quiet conclusion drawn by the universe itself. Not a conclusion in the sense of finality, but a statement about how far complexity can stretch before it becomes something else entirely. The star no longer reads as an object to be measured, compared, or ranked. It reads as a condition, a temporary arrangement of matter that exists precisely because the universe allows arrangements to exist without demanding they remain tidy. At this stage, the usual questions fade. How big is it? How massive? How long will it last? These questions still have technical answers, but they no longer feel central. What matters now is what happens when scale outgrows structure, when extension overtakes cohesion, and when an object becomes so large that its identity depends more on persistence than definition. Stephenson, too, 18, exists in that space. It is not held together by strength but by delay. Forces that would normally resolve instability are slowed by distance. Feedback that would normally regulate growth is softened by diffusion. Collapse that would normally unify the star is postponed because information cannot travel fast enough to synchronize the whole. The star survives because the universe does not rush its own processes. This slowness is not inefficiency, it is a feature of scale. As systems grow larger, they inherit time. Time becomes an active ingredient. Processes stretch, responses lag, and contradictions coexist longer than intuition expects. Stephenson, too, 18 embodies this inheritance of time more clearly than almost any other known star. In smaller stars, imbalance is corrected quickly. In this star, imbalance becomes a long-lived state. Expansion and loss, pressure and gravity, coherence and fragmentation all operate simultaneously without resolving into a single outcome. The star does not choose a direction, it drifts. This drifting reframes how we think about cosmic evolution. Evolution is often imagined as a sequence of decisive steps: formation, stability, collapse. Stephenson, too, 18, suggests a different pattern, one where the middle stretches, where the transition itself becomes the dominant phase. The star spends much of its existence not becoming something else, but remaining suspended between states. Suspension at this scale has consequences. It creates environments rather than objects, regions rather than points. The star's outer layers interact with surrounding space in ways that blur the line between stellar interior and interstellar medium. Matter flows outward slowly, mixing with dust and gas that may one day become part of entirely different systems. In this way, Stephenson 2-180 is already dissolving even as it exists. Its boundaries are porous, its material is not fully contained. The star is less a closed system than a leaking one, contributing to the future while still present in the now. This leakage is not loss in the ordinary sense, it is redistribution. The star does not vanish all at once. It spreads itself thin, extending its influence across space and time. Even before its end, it is already shaping what will come after. That shaping is subtle but profound. The heavy elements forged in its core will seed future stars and planets. The energy it releases will stir surrounding clouds. The void it leaves behind will alter gravitational balances. Stephenson 2.18 is not an endpoint. It is a transition state in a much larger cycle. Understanding this cycle dissolves the temptation to treat the star as exceptional in isolation. It is exceptional in scale but not in role. Like all massive stars, it participates in the long transformation of matter across cosmic time. Its difference lies in how dramatically it stretches that participation speed. This stretching forces a re-evaluation of what it means for something to exist in the universe. Existence is often imagined as a stable condition, an object with clear boundaries persisting over time. Stephenson 2.18 challenges that image. It exists as a gradient, as a process, as a temporary convergence of conditions rather than a discrete entity. This view aligns with a deeper truth about reality. At fundamental levels, everything exists as process. Particles are excitations, fields fluctuate. Structures emerge and dissolve. What we call objects are patterns that persist long enough to be named. Stephenson 2.18 is a pattern stretched almost to the breaking point. Seeing the star this way removes the urge to mythologize it. It does not need to be framed as monstrous or terrifying. Its scale is not a threat. It is simply the natural outcome of mass, time, and permissive physics interacting without constraint. The universe did not set out to create the largest star imaginable. It allowed conditions under which such a star could form, inflate, and persist briefly. Nothing more, nothing less. This lack of intention is crucial. It strips the star of narrative drama and replaces it with something quieter and more honest. The universe is not telling a story through Stephenson 2.18. It is expressing a possibility. Possibilities by their nature do not need justification. They only need permission. Stephenson 2.18 exists because permission was granted by physics. That permission did not include longevity. It did not include clarity. It did not include stability. It included only consistency with fundamental law. And that is enough. This realization shifts the emotional tone of the star. Instead of awe mixed with confusion, what emerges is a kind of calm respect. Respect for a universe that does not rush to correct itself. Respect for a system that allows extremes to unfold without commentary. Stephenson 2.18 does not ask to be understood. It does not demand attention. It does not announce its presence loudly. It simply occupies space at a scale that makes ordinary understanding uncomfortable. In doing so, it invites a different relationship with knowledge, one that is less about mastery and more about coexistence. Some phenomena are not meant to be fully internalized. They are meant to be acknowledged as real even when they exceed mental representation. This acknowledgement is not defeat, it is maturity. Science reaches maturity not when everything is explained away, but when it learns how to live with unresolved complexity. Stephenson 2.18 is a teacher in this sense. It teaches restraint, it teaches patience, it teaches the value of letting questions remain open. The star will not last, it will collapse, disperse, or vanish from relevance as all stars do, but the shift it induces in perspective will persist. It will remain as a reference point, a reminder of how far scale can stretch before concepts dissolve. Long after the star is gone, its lesson will remain embedded in how astronomy approaches extremes, in how models are framed, in how limits are treated, in how humility is preserved in the face of vastness. Stephenson 2. 1.8 will not be remembered because it was the largest forever. It will be remembered because it marked the place where size stopped behaving like size and started behaving like a challenge to understanding itself. And in that quiet challenge, the universe revealed something essential, that reality does not need to be comprehensible to be consistent, and that the most honest response to the extreme is not explanation but attention. Attention without urgency, attention without expectation, attention that allows something vast, diffuse and temporary to exist without forcing it into familiar shapes. Stephenson 2. 1.8 exists in that allowance, and by encountering it, understanding does not close. It opens, gently, indefinitely, into a universe that is larger, softer, and far less obligated to clarity than the mind once assumed. As the final perspective unfolds, Stephenson 2. 1.8 recedes from view not because it becomes less important, but because its lesson has already been absorbed. What remains is not the star itself, but a shift in how scale, endurance, and understanding are approached. The star's presence has quietly altered the background assumptions against which all other cosmic objects are interpreted. At this stage, the most striking realization is how ordinary the star becomes once the shock of its size fades. Not ordinary in magnitude, but ordinary in principle. Stephenson 2. 1.8 obeys the same rules as every other star. It burns fuel, it loses mass, it evolves. Nothing about its physics is exceptional in isolation. What is exceptional is the combination, the way familiar processes accumulate and interact when allowed to operate across extreme distances and times. This accumulation reveals a core truth. Complexity does not always arise from new mechanisms. Often, it emerges when ordinary mechanisms are allowed to compound without constraint. Stephenson 2. 1.8 is not exotic because it introduces something new, but because it refuses to stop doing what stars always do, expanding, reacting, adjusting, long after intuition expects limits to intervene. This refusal exposes the difference between physical limits and cognitive limits. Physical limits are enforced by conservation laws, by stability thresholds, by energy balance. Cognitive limits are enforced by expectation, by habit, by the scales we are accustomed to navigating. Stephenson 2. 1.8 crosses the latter without violating the former. Understanding this distinction matters. It prevents the mistake of interpreting discomfort as impossibility. Just because something feels too large, too diffuse, or too unstable to exist does not mean it cannot. The universe does not consult feeling, it consults law. This realization has consequences for how future discoveries will be received. As observational tools improve, objects even more extreme than Stephenson 2, 1.8 may come into view. They may not resemble traditional stars at all. They may occupy categories not yet named. When they appear, the lesson of Stephenson 2, 1.8 will matter. That unfamiliarity is not evidence of error. The star also reframes how progress in science is measured. Progress is often imagined as increasing precision, tighter measurements, narrower error bars, more exact predictions. Stephenson 2, 1.8 suggests another kind of progress, the ability to tolerate uncertainty without paralysis. At extremes, precision alone is insufficient. One must also accept ambiguity. Ambiguity here is not ignorance, it is resolution, acknowledging scale. When boundaries blur, insisting on sharp definitions can distort understanding. Stephenson 2. 1.8 teaches that sometimes the most accurate description is one that remains flexible. This flexibility applies not only to stars but to how the universe is conceptualized as a whole. The cosmos is often portrayed as a set of discrete objects embedded in empty space. In reality, it is a continuum of influence, density, and interaction. Stephenson 2. 1.8 makes that continuum visible within a single star. The star's extended envelope, gradual boundaries, and slow internal communication show that even objects we label as singular entities are often regions of gradual transition. Space does not begin abruptly where the star ends. Time does not advance uniformly throughout its interior. Identity itself becomes distributed. This distributed identity dissolves the temptation to treat cosmic objects as static landmarks. Stephenson 2:18 is not a landmark. It is a moment, a configuration that exists briefly, shaped by conditions that will not persist. Seeing the star as a moment rather than a monument alters its emotional weight. It becomes less about awe and more about timing. The universe happened to produce this configuration while observers existed to notice it. That coincidence is not guaranteed. Many such configurations likely arise and vanish without ever being seen. This perspective removes the sense that the universe is performing for observation. It is not. Observation is incidental. Stephenson 2:18 does not exist because it can be measured. It exists because nothing prevented its formation at that time and place. This indifference is not bleak, it is liberating. It frees understanding from the need to assign purpose. The star does not need to matter in a grand narrative sense. It matters because it expands the range of known behavior. In expanding that range, Stephenson 2:18 quietly reshapes what is considered normal. After encountering it, other large stars feel less surprising. Extremes feel less threatening. The envelope of expectation stretches. This stretching is cumulative. Each extreme encountered makes the next one easier to accept. Over time, the universe becomes less mysterious not because it is reduced, but because tolerance for scale increases. Stephenson 2:18 contributes to that tolerance. The star also reframes the relationship between observation and humility. It demonstrates that the universe can be consistent without being comprehensible in familiar terms. Accepting that consistency does not require full comprehension is a form of intellectual maturity. This maturity allows science to proceed without demanding closure. It allows questions to remain open without undermining confidence in underlying principles. Stephenson 2:18 reinforces this stance simply by resisting simplification. As attention finally drifts away, what lingers is not the image of a vast star, but the recognition that scale itself is not something to be conquered. It is something to be accommodated. Understanding does not mean shrinking reality to fit the mind. It means expanding the mind's tolerance for what cannot be easily pictured. Stephenson 2:18 leaves behind no warning, no message, no directive. It leaves behind an adjustment, a subtle recalibration of expectation. After it, the universe feels less obligated to remain within comfortable bounds, and that adjustment persists. The star may collapse, disperse, or fade into obscurity. Its material will mix with the galaxy, its energy will dissipate, its name may eventually disappear from catalogues, but the shift it produced in how extremes are approached will remain embedded in the practice of astronomy. In that sense, Stephenson 2:18 does not need to endure to matter. Its influence does not depend on longevity, it depends on encounter. The encounter has already happened. What remains is a universe that feels slightly larger, slightly less constrained, and slightly more honest about its indifference to human scale. Stephenson 2:18 does not stand as a boundary marking where the universe stops making sense. It marks where the demand for sense-making must change, not towards certainty, but toward patience. Patience with scale, patience with ambiguity, patience with a reality that does not owe understanding anything beyond consistency. And in accepting that, the universe becomes not smaller or more distant, but calmer, a place where extremes exist not to be mastered, but to be acknowledged as part of a vast continuum that unfolds quietly, without commentary across time. Stephenson 2:18 occupies one point along that continuum, not as an endpoint, but as a reminder that the universe is far more permissive than imagination and far less concerned with comfort than curiosity, and that, ultimately, is enough. As the exploration reaches its quiet end, Stephenson 2.18 no longer feels like something separate from the rest of the universe. It dissolves back into the wider cosmic context from which it emerged, leaving behind not a sense of completion, but a softened understanding of how reality behaves when it is allowed to stretch without restraint. The star does not conclude a story, it gently fades into a realization. What Stephenson 2.18 ultimately shows is that the universe does not operate on thresholds that snap shut. There is no precise moment where scale becomes too much and reality intervenes. Instead, there are gradients of viability, long slopes where existence becomes harder, slower, thinner, but not immediately impossible. The star lives on that slope, occupying a region where endurance replaces stability and persistence replaces balance. This distinction matters. Stability suggests something meant to last. Endurance suggests something allowed to last, even if only briefly. Stephenson 2.18 endures. It persists not because it is favoured, but because the universe does not rush to remove what still functions. In that sense, the star is deeply honest. It does not pretend to be permanent. It does not resolve its contradictions. It simply continues until continuation is no longer supported. There is no drama in this process, no climax, no sudden revelation, just gradual change unfolding according to rules that never cared about narrative. This honesty strips away the temptation to romanticize extremes. Stephenson 2.18 is not heroic. It is not defiant. It is not tragic. It is matter behaving as matter does when given enough mass, enough time, and enough freedom from immediate constraint. And that is precisely why it matters. The star's existence clarifies something easy to forget. The universe is not engineered to make sense to observers. It is not designed to produce objects that align with intuition. Intuition is a local adaptation, tuned to small scales and short times. Stephenson 2.18 exists, far outside that tuning. Accepting this is a form of intellectual humility. It means recognizing that discomfort does not signal error. Confusion does not signal impossibility. Some phenomena are meant to be approached indirectly, understood statistically, and accepted without full mental visualization. Stephenson 2 vastly encourages that acceptance. It also reframes how wonder operates. Wonder is often associated with spectacle, explosions, collisions, violence, but this star invites a quieter wonder, the wonder of persistence without emphasis, the wonder of something existing simply because it can. There is something profoundly calming in that. The star does not rush. It does not announce itself. It does not demand attention. When it exists at its own pace, following processes that unfold too slowly and too broadly to feel urgent. This calm stands in contrast to human narratives, which tend to compress time and sharpen edges. We look for beginnings and endings. Stephenson 2.18 exists mostly in between, in the long middle where nothing decisive happens, yet everything meaningful unfolds. That long middle is where much of the universe resides. By spending time with an object like this, perception subtly shifts. The universe stops feeling like a sequence of events and starts feeling like a continuous condition. Change becomes something that happens gradually, unevenly, and without clear markers. This shift carries a quiet implication. Not everything that matters will be dramatic. Not everything that changes the way understanding works will announce itself loudly. Some of the most important lessons arrive slowly, through extended exposure rather than sudden insight. Stephenson 2.18 teaches in this way. It teaches by existing long enough to be noticed, then lingering long enough to unsettle assumptions. It teaches by refusing to collapse neatly into familiar categories. It teaches by stretching patience, and patience, at cosmic scale, is not passive. It is an active stance, a willingness to observe without forcing resolution, a willingness to let understanding remain incomplete. This stance is increasingly important as exploration moves deeper into extreme regimes. Larger telescopes, deeper surveys, and longer baselines will continue to reveal objects that resist intuition. Stephenson 2.18 is not the last of its kind. It is an early signal of what lies ahead. Future discoveries may push scale even further. They may reveal stars, structures, or phenomena that make Stephenson 2.18 feel modest by comparison. When that happens, the lesson of this star will matter even more. That understanding does not require shrinking reality to fit expectation. It requires expanding expectation to fit reality. This expansion does not eliminate mystery. It reframes it. Mystery becomes not a problem to be solved, but a feature to be navigated. Stephenson 2.18 does not remove mystery from stellar physics. It relocates it, from questions of possibility to questions of tolerance. How much imbalance can persist? How long can coherence survive at extreme scale? How softly can collapse arrive? These questions do not demand immediate answers. They invite continued attention. As the star eventually fades, collapsing, dispersing, or transforming into something else, its physical presence will end. But its conceptual presence will remain. It will continue to sit quietly in the background of astronomical thought, a reminder that the universe allows more than intuition expects. In that sense, Stephenson 2.18 is not a destination. It is a waypoint, a marker passed along the path of understanding, indicating where familiar frames begin to loosen. Beyond that marker, explanation must slow down. Beyond it, certainty becomes conditional. Beyond it, scale stops being something that can be easily grasped and becomes something that must be accommodated. The star does not tell us where that path leads. It does not offer a conclusion. It does not resolve into a final insight. It simply shows that the path continues, and perhaps that is the most fitting ending possible. Not a summary, not a conclusion, but an openness. A recognition that understanding is not a finite resource to be exhausted, but a posture that adapts as reality reveals more of itself. Stephenson 2.18 stands as a quiet demonstration of that posture. It exists without apology. It stretches without explanation. It endures without promise. And in encountering it, understanding does not arrive at certainty. It arrives at calm. A calm acceptance that the universe is larger, softer, and less obligated to clarity than the mind once assumed, and that this is not a failure of understanding, but its natural evolution. In that calm, Stephenson 2.18 fades gently from focus, not because it has been fully understood, but because it has already done what it needed to do. It expanded the space in which understanding can exist, and that expansion remains. As the final extension of this reflection unfolds, Stephenson 2.18 settles into a different kind of presence, not as something to be examined further, but as something that quietly reshapes how absence, distance, and scale are felt. At this point, the star no longer challenges knowledge directly. Instead, it alters the emotional geometry of understanding itself. What lingers after everything measurable has been discussed is a subtle shift in expectation. The universe begins to feel less like a collection of dramatic milestones and more like a continuous field where extremes arise naturally, briefly, and without announcement. Stephenson 2.18 fits into this field not as a climax, but as a calm outgrowth of permissive physics. This calm is important. It counters the instinct to frame cosmic extremes as exceptional moments that demand attention. In reality, the universe produces such extremes quietly as side effects of long, unremarkable processes. Dense clouds collapse, mass accumulates, fusion ignites. Expansion follows. No step is extraordinary on its own. What becomes extraordinary is only the cumulative result. Stephenson 2.18 is that cumulative result. This realization removes the temptation to search for intention behind the star's existence. It was not meant to be this large. It did not arise to test theories or redefine limits. It simply followed the path that unfolded when conditions aligned without interruption. The universe did not stop it because nothing required it to stop. In this way, the star becomes a reminder that the cosmos is not conservative with possibility. It does not ration scale. It does not impose elegance. It allows systems to drift toward extremes until forces finally intervene, not to correct excess, but to conclude it. Conclusion here is not resolution, it is exhaustion. The gradual reaching of conditions where continuation is no longer supported. Stephenson 2.18 has not yet reached that point, but it moves toward it slowly, quietly, without drama. This slow movement reframes the idea of endings. Endings are often imagined as sudden, definitive events. In reality, many endings are processes that unfold across long spans, invisible until they are nearly complete. Stephenson 2.18 is already ending, even as it exists. Mass is being lost. Energy is dispersing. Coherence is thinning. The star does not collapse all at once. It unwinds. This unwinding is not failure. It is the natural arc of any system pushed far from equilibrium. The universe does not punish imbalance. It allows imbalance to play out until it cannot sustain itself. Stephenson 2.18 is living through that allowance. Seeing the star in this light dissolves any remaining sense of urgency. There is no rush to understand it fully before it vanishes. Its importance does not depend on being fully decoded. It has already contributed what it can contribute, a demonstration of tolerance. Tolerance for size, tolerance for inefficiency, tolerance for ambiguity. These tolerances are not just properties of the universe. They become tools for understanding it. Stephenson 2.18 subtly teaches that comprehension does not require domination. It does not require capturing every detail. Sometimes comprehension is simply recognizing that a system behaves differently because it exists at a scale where familiar instincts no longer apply. This recognition frees understanding from anxiety. There is no need to force clarity where clarity is not natural. There is no need to compress reality into digestible metaphors. The universe does not demand that. The star also invites reflection on how knowledge ages. At one time, the largest known star would have felt definitive. Later discoveries may eclipse Stephenson 2.18. When that happens, the star's factual distinction may fade, but its conceptual role will remain. Because the lesson it provides is not tied to being the largest, it is tied to being large enough to disrupt expectation. Even if a larger star is discovered, it will not erase what Stephenson 2.18 already revealed. It will build upon it. It will push tolerance further. The universe will continue this pattern indefinitely, always staying slightly ahead of intuition. This endless expansion of scale mirrors the expansion of the universe itself. Space grows, distances stretch, horizons recede. There is no final vantage point from which everything becomes clear. Understanding must adapt continuously. Stephenson 2.18 is one adaptation point along that path. It marks a moment when understanding had to soften, when rigidity gave way to patience, and certainty gave way to openness. These shifts are not temporary, they persist, shaping how future phenomena are approached. In this sense, the star's greatest impact is invisible. It resides in the quiet recalibration of expectations. After encountering Stephenson 2.18, it becomes easier to accept that the universe may contain structures that are awkward, inefficient, and only briefly coherent. That acceptance reduces surprise without diminishing wonder. Wonder changes form. It becomes less about shock and more about continuity. Less about extremes as spectacles and more about extremes as natural outcomes of time and mass interacting without oversight. Stephenson 2.18 belongs fully to that continuity. As attention finally releases its grip on the star, what remains is not a lingering image but a posture, a way of relating to scale that does not insist on comfort. a posture that allows reality to remain larger than understanding without interpreting that gap as failure. This posture is valuable beyond astronomy. It applies to any attempt to understand systems larger than the observer: climates, ecosystems, histories, even civilizations. Scale changes behavior. Patience becomes essential. Certainty becomes conditional. The universe, through Stephenson 2:18, demonstrates this without instruction. It simply shows what happens when mass is allowed to gather, expand, and persist without being forced into tidy proportions. It shows that reality does not need to be efficient to be lawful. It does not need to be comprehensible to be consistent. Stephenson 2:18 exists at the intersection of those truths. It is lawful but not intuitive, consistent but not tidy, real but difficult to picture, and that is enough. There is no final insight to extract, no summary that completes the thought. The star resists closure because closure implies a boundary, and boundaries are precisely what it dissolves. Instead, there is only a gentle settling, an understanding that some objects are important not because they can be fully understood, but because they reveal how understanding must change when scale outpaces familiarity. Stephenson 2:18 has done that work. It has expanded the conceptual space in which reality is allowed to exist, and as it continues quietly toward its own conclusion, that expanded space remains open, patient, and unhurried, waiting for whatever extreme the universe allows next, not with anticipation, but with readiness. As this final layer of reflection unfolds, Stephenson 2:18 becomes less a subject of astronomy and more a quiet reference point for how reality behaves when it is no longer constrained by familiarity. By now, the star has ceased to feel extraordinary in the emotional sense. Its size no longer shocks, its instability no longer unsettles. What remains is a calm recognition that the universe routinely produces conditions that sit far outside the range of everyday understanding, and that this is not an exception but the norm at sufficient scale. At this stage, the most important shift is not intellectual but perceptual. The universe begins to feel less like a place filled with objects and more like a continuous process in which objects briefly appear. Stephenson 2:18 is one such appearance, a configuration of matter that holds together just long enough to be noticed, then gradually dissolves back into the larger flow. This process-oriented view changes the emotional relationship with scale. Instead of reacting with awe or disbelief, the response becomes acceptance. The star is not asking to be admired, it is not challenging the observer. It is simply occupying a permitted state within a vast range of possible states. That permission is the key idea that lingers. The universe does not actively pursue extremes, but it does not avoid them either. Given enough time and enough space, matter explores what it is allowed to do. Sometimes that exploration produces stars of ordinary size. Sometimes it produces objects so extended that they blur the line between structure and environment. Stephenson 2:18 belongs to the latter category. Its existence underscores a subtle truth. The universe is not optimized for efficiency or clarity, it is optimized for consistency. As long as the fundamental rules are not violated, outcomes are allowed to persist, even if they are awkward, unstable, or short-lived. This tolerance for awkwardness is deeply instructive. It suggests that order in the universe is not imposed from above, but emerges locally where conditions favor it. Elsewhere, disorder, diffusion, and imbalance are permitted to linger. Stephenson 2:18 is not an ordered system in the traditional sense. It is loosely organized, internally delayed, and constantly leaking material. And yet, it exists. This existence reframes how stability is defined. Stability is often confused with permanence, but permanence is rare in the universe. What is common is persistence, the ability of a system to maintain identity for a time, even while slowly unraveling. Stephenson 2:18 persists. Persistence does not require symmetry. It does not require elegance. It requires only that disintegration proceeds more slowly than coherence fails. For now, that condition holds. This reframing also dissolves the urge to ask whether the star is too big. That question assumes a normative scale, a preferred size against which deviation is judged. The universe does not operate with such preferences. It allows size to grow until other processes intervene. Stephenson 2:18 is not too big. It is as big as conditions allowed. This acceptance removes moral language from scale. The star is not excessive. It is not irresponsible. It is not reckless. Those are human judgments. The universe recognizes only allowance and consequence. Allowance produced Stephenson 2:18. Consequence will eventually remove it. Between those two lies a long, quiet interval of existence. That interval is where understanding now rests. The star also gently dismantles the idea that the most important phenomena must be central or dominant. Stephenson 2:18 does not shape the fate of its galaxy. It does not anchor cosmic structure. It does not influence space-time on grand scales. And yet, it matters because it stretches the envelope of what is known. Its importance is epistemic rather than causal. It changes how knowledge is framed rather than how matter moves. This kind of importance is easy to overlook, but it is foundational to progress. By encountering objects that strain intuition, science is forced to evolve. Models become more flexible, language becomes more careful, assumptions are exposed. Stephenson 2:18 serves this function quietly without demanding attention. In doing so, it reveals something else, that the universe does not need to be dramatic to be instructive, does not rely on explosions or catastrophes to teach. Sometimes instruction arrives through prolonged exposure to something that simply refuses to fit neatly into expectations. This refusal is not antagonistic, it is indifferent, and indifference, when recognized, can be strangely comforting. It removes the sense that understanding is a contest to be won. Instead, understanding becomes a relationship, one in which the observer adjusts to reality rather than attempting to force reality into familiar shapes. Stephenson 2:18 invites this adjustment. It invites a slowing down of interpretation, a willingness to let go of sharp boundaries, a readiness to accept that some systems exist in states that are neither stable nor collapsing, neither coherent nor chaotic, but something in between. That in between is not a failure of classification, it is a feature of scale. As systems grow larger, their states become less discrete. Transitions blur, phases overlap. Stephenson 2:18 lives in that overlap. It is neither a typical star nor something entirely different. It is a star stretched into a regime where the word itself begins to feel approximate. Approximation at this level is not weakness, it is honesty. The universe does not operate with perfect categories. It operates with continua. Stephenson 2:1b8 makes that visible. As this understanding settles, there is no urge to push further, to extract one more conclusion. The star does not offer one. It offers presence rather than message. Presence is enough. The star's eventual disappearance will not negate what it revealed. Its lesson does not depend on survival. It depends on encounter. Once encountered, it alters the baseline of expectation permanently. After Stephenson 2:18, the universe feels more permissive, less constrained, more tolerant of forms that feel awkward or excessive. That tolerance changes how future discoveries are approached. Instead of asking, how can this exist? The question becomes, what conditions allowed this to exist, and for how long? That shift is subtle, but transformative. It moves understanding away from disbelief and toward contextualization, away from judgment and toward description, away from the need for comfort and toward acceptance of scale as it is. Stephenson 2:18 does not need to be remembered as the largest star. It needs to be remembered as the star that made scale feel negotiable, not fixed, not final, but dependent on time, condition, and perspective. And in that negotiation, understanding grows quieter, steadier, and more patient. The universe remains vast, reality remains indifferent, and within that indifference, objects like Stephenson 2.18 arise, persist briefly, and fade, leaving behind not answers but a widened space in which questions can exist without urgency. That space is the true legacy of Stephenson 2.18, not a record. Not a spectacle, but a gentle expansion of what the mind is willing to accept as real. As the final quiet stretch unfolds, Stephenson 2.18 no longer needs to be approached as an object at all. By now, it has become something subtler, a reference frame against which understanding itself has been recalibrated. The star does not remain at the center of attention. Instead, it dissolves into the background, where its influence is no longer direct but structural. It has altered the way scale is felt, and that alteration remains even as focus drifts elsewhere. At this point, the most meaningful realization is how unremarkable the universe's response to such an extreme truly is. There is no cosmic hesitation, no instability rippling outward in alarm, no correction imposed from above. Stephenson 2.18 exists, and the universe simply allows it to exist. This allowance is neither approval nor indifference in the emotional sense. It is neutrality in its purest form. Neutrality is often mistaken for emptiness, but it is anything but. Neutrality is what allows diversity to emerge. It is what permits matter to explore its own limits without interference. Stephenson 2.18 is a product of that neutrality. It is not a special case singled out by fate. It is a natural consequence of conditions unfolding without interruption. This realization reframes how significance is assigned. The star is not significant because it changes the universe. It is significant because it reveals how the universe doesn't change in response to extremes. There is no recalibration, no adjustment. The same rules apply whether a star is modest or vast beyond intuition. This consistency is the quiet foundation of reality. It means that even when scale becomes uncomfortable, law remains steady. Gravity does not become confused. Fusion does not behave differently because size feels excessive. Energy still flows according to the same principles. Stephenson 2.18 exists not because the universe made an exception, but because no exception was required. Understanding this dissolves the last temptation to treat the star as a boundary marker. It is not the edge of possibility. It is simply a point along a continuum that extends further than imagination has yet followed. If conditions allow something larger, then something larger will exist. Briefly, quietly, without ceremony. The universe does not cap its creations for the sake of coherence. It allows coherence to fail gradually. Stephenson 2.18 illustrates how failure itself can be extended. Instead of collapsing the moment stability weakens, the star enters a long twilight where existence is maintained through delay and diffusion. This twilight is not dramatic. It is slow, gentle, almost imperceptible. In this sense, the star teaches something subtle about endings. Endings are rarely singular moments. They are phases, long periods during which identity thins before disappearing entirely. Stephenson 2.18 is already in such a phase. It is ending even as it exists. But this ending does not negate presence. It redefines it. Presence, at cosmic scale, does not require permanence. It requires duration. A system only needs to persist long enough to interact, to influence, to be part of the ongoing transformation of matter. Stephenson 2.18 has already done this. Its material is drifting outward. Its energy is diffusing. Its future influence is already being written into surrounding space. The star is not waiting to matter. It already has. And this leads to the most settled understanding of all, that the universe does not measure importance by longevity, clarity, or stability. It measures nothing at all. Importance is an observer's construct, layered onto processes that continue regardless. Stephenson 2.18 does not know it is large. It does not experience its own scale. It does not react to the difficulty of being understood. It simply exists within conditions that permit its current state. That simplicity is deeply grounding. It strips away the impulse to dramatize extremes. The star does not loom. It does not threaten. It does not astonish on its own terms. Astonishment arises only when the mind insists on framing reality relative to itself. When that insistence softens, what remains is calm observation, calm acceptance, calm acknowledgement that reality does not need to align with comfort to remain lawful. Stephenson 2:1-8 is a reminder that the universe is not built around observers. Observers arise within it briefly during periods when scale and complexity intersect in ways that support awareness. Outside those periods, the universe continues unchanged. This understanding carries a quiet humility. It reminds us that perception is local, temporary, and conditional. The universe is not obligated to preserve it, and yet, within that indifference, moments of recognition occur. Stephenson 2:1-8 is one such moment, not because it was meant to be seen, but because it happened to exist when seeing was possible. This coincidence does not require meaning to be valid. It requires only acknowledgement. As attention finally releases even this last thread, Stephenson 2:1-8 settles into the broader tapestry of cosmic history. It becomes one event among countless others, no longer emphasized, no longer isolated. Its uniqueness fades, but its lesson remains embedded. The lesson is not about size. It is about permission. The universe permits far more than intuition expects. It permits imbalance. It permits inefficiency. It permits objects that strain coherence without immediately destroying it. It permits scale to stretch into regions where understanding must adapt or fall silent. Stephenson 2:1-8 occupied one of those regions. It did not need to explain itself. It did not need to justify its existence. It simply existed, briefly, quietly, consistently. And in encountering it, understanding did not arrive at a conclusion. It arrived at equilibrium, an equilibrium between curiosity and acceptance, between explanation and restraint, between the desire to know and the willingness to let reality remain larger than comprehension. That equilibrium is the true ending of this journey, not a final answer, not a closing statement, but a settled awareness that the universe continues, permissive, indifferent, and vast, whether or not understanding keeps pace. Stephenson 2:1-8 fades from focus now, not because it has been exhausted, but because it has already done what it needed to do. It expanded the space in which understanding can exist, and that space remains open, quiet, and ready for whatever extreme reality allows next. As everything settles, there is no final revelation waiting beyond Stephenson 2:1-8. No hidden truth, no concluding message written into the star itself. What remains is quieter than that, a steady awareness of how reality behaves when it is allowed to unfold without needing to be understood. Stephenson 2:1-8 does not resolve into meaning. It dissolves into context. It reminds us that the universe is not a sequence of answers, but a continuous allowance. Matter gathers, expands, destabilizes, and redistributes itself according to rules that never pause to ask whether the outcome feels reasonable. Scale grows when nothing stops it. Scale fades when continuation is no longer supported. There is no preference, no intention, no correction beyond consequence. By the time attention leaves this star, it no longer feels necessary to hold on to its measurements or rankings. Those were tools to approach it, not what it ultimately offered. What it offered instead was a change in posture, a calmer way of relating to extremes. The universe does not rush, it does not optimize, it does not explain itself. It allows. Stephenson 2:1-8 existed because allowance lasted long enough. It will disappear because allowance will eventually shift. Nothing more dramatic than that is required, and in that simplicity something settles. Understanding does not need to conquer scale. It does not need to compress it. It only needs to remain open enough to let scale exist without resistance. The star fades back into the galaxy. Its material continues on. Its influence spreads thin. Its name will eventually be replaced by others. But the adjustment it caused remains. A quiet recalibration of expectation. A softened boundary between what feels imaginable and what simply is. There is no ending beyond this. Only continuation. The universe remains. Scale remains. Reality unfolds at its own pace, and listening, slowly, patiently, is enough.